Hello there, and welcome to Science for Sleep, where curiosity gets comfortable, ideas wander gently through the universe, and science takes the scenic route toward rest. Tonight we're going to explore something so enormous that even astronomers sometimes pause, stare at their maps and quietly say, wait, that can't possibly be the whole thing. Because the universe, as it turns out, is not arranged the way people once imagined. It isn't simply a random sprinkle of galaxies drifting through empty darkness like glitter tossed into the air. When scientists began mapping the cosmos carefully, they discovered something far stranger and far more beautiful in its quiet complexity. Galaxies, the vast cities of stars that fill the universe, appear to gather along immense strands that stretch across space for hundreds of millions of light years. These strands intersect, twist and branch, forming an enormous network that astronomers now call the cosmic web. It's a structure so large that it shapes the entire visible universe, and tonight we're going to take a slow and relaxed journey through it. But before we drift too far into the depths of space, I'd love to ask you something simple. Where in the world are you listening from tonight, and what time is it there right now? Perhaps it's late evening where you are. Maybe the room is quiet, the lights are dim, and the day is finally beginning to wind down. Or perhaps you're listening earlier in the night, settling in with a cup of tea or just letting your thoughts slow down after a long stretch of work or study. Wherever you are, and whenever this moment happens to be on your personal timeline, I'm glad you're here. And if you find these quiet explorations soothing, interesting, or simply a pleasant way to relax before sleep, you might consider giving the video a like or subscribing to the channel. It helps this small corner of calm science reach more curious minds who might appreciate a gentle journey through the universe before drifting off. Now, let's begin. Imagine, just for a moment, that you could step outside our galaxy and look at the universe from a very great distance. Not just a little farther than the Moon or Mars, not even just outside the Milky Way. Imagine travelling far enough away that entire galaxies become tiny points of light. If you looked around from that vantage point, you might expect to see galaxies scattered evenly in every direction, something like stars on a clear night. For a long time, that was roughly how scientists pictured the universe. Galaxies were thought to be sprinkled through space somewhat randomly. Some areas might contain more galaxies, some fewer, but overall the cosmos would look fairly uniform if you zoomed out far enough. And to be fair, this idea wasn't unreasonable. When astronomers first began studying galaxies in the early 20th century, their observations were limited. Telescopes were powerful enough to see many galaxies, but not powerful enough to map huge portions of the universe in detail. Picture trying to understand the layout of an entire forest, while standing in the middle of it with a flashlight. You might see a few trees nearby, maybe a clearing here or there, but the larger pattern would remain hidden. Early astronomers were in a similar situation. They could observe individual galaxies and small groups of galaxies, but the grand structure of the cosmos was still concealed. And then, slowly technology improved. Telescopes grew larger, cameras became more sensitive. Computers began helping astronomers collect and analyze enormous amounts of data. Instead of studying a handful of galaxies at a time, scientists could begin surveying tens of thousands, then hundreds of thousands, eventually millions. What they discovered was surprising. Galaxies did not appear to be scattered randomly at all. Instead, they seemed to gather in clusters. Clusters of galaxies had been known for a while. Even early observers noticed that some galaxies tended to group together under the pull of gravity. Our own galaxy, the Milky Way, lives in one such group called the local group, which contains dozens of galaxies bound together by gravity. But as astronomers expanded their surveys, they began noticing something even larger. Clusters themselves appeared to gather into even bigger structures called superclusters. These superclusters were enormous collections of galaxy clusters stretching across vast regions of space. At first glance, this might not sound too surprising. Gravity naturally pulls matter together, so larger groupings were expected. But the real surprise appeared when scientists began mapping the positions of galaxies in 3 dimensions. Instead of simply plotting galaxies on the sky, astronomers measured their distances as well. This allowed them to create detailed maps showing where galaxies actually sat within the universe. When these maps were visualized, something remarkable emerged. Galaxies did not fill space evenly. Instead, they formed long, thin strands. These strands connected clusters and superclusters together like threads tying beads on a necklace. Between the strands were enormous regions that contained almost no galaxies at all. These regions are called cosmic voids. Imagine blowing soap bubbles inside a sink full of foam. The bubbles push against one another, forming thin walls where they meet, while large empty spaces appear inside each bubble. The distribution of galaxies in the universe turns out to look surprisingly similar. The strands of galaxies form the walls and edges, while the vast voids between them remain mostly empty. When astronomers saw the first clear maps of this structure, the pattern was unmistakable. The universe resembled a web. Not a spider web exactly, but something closer to a vast three-dimensional network of filaments stretching across unimaginable distances. And so the name stuck, the cosmic web. Now here's the astonishing part. The scale of this structure is almost impossible to comprehend. Individual galaxies like the Milky Way are already enormous. Our galaxy contains hundreds of billions of stars and stretches about 100,000 light-years across. Yet within the cosmic web, galaxies are merely tiny building blocks. Clusters of galaxies may contain hundreds or even thousands of galaxies bound together by gravity. Superclusters stretch even farther, spanning hundreds of millions of light-years, and the filaments connecting them can run for distances that dwarf almost anything else in the universe. Some of these filaments extend for more than 1 billion light-years. To give that number some perspective, a light-year is the distance light travels in 1 year, moving at about 300,000 kilometers per second. Light from the Sun takes about 8 minutes to reach Earth. Light from the nearest star beyond our Sun takes more than 4 years. A filament 1 billion light-years long means that even travelling at the speed of light, it would take 1 billion years to cross from one end to the other. And yet these enormous structures are not rare. They are the framework of the universe itself. If you could somehow step back far enough to see the entire observable universe, you would likely see an immense network of glowing strands. Clusters of galaxies would sit at the intersections of these strands, like knots tying the web together. Between them would lie gigantic voids stretching across hundreds of millions of light-years, regions where galaxies are incredibly sparse. And somewhere inside one of those strands sits our own galaxy. Right now, as you listen, the Milky Way quietly drifts along within this cosmic structure, orbiting through space along with billions of other galaxies. But none of this was obvious at first. In fact, the discovery of the cosmic web took decades of careful observation, data analysis, and patient mapping. During the 1970s and 1980s, astronomers began conducting large galaxy surveys designed specifically to understand the large-scale structure of the universe. One famous project was the CFA Redshift survey, which mapped the positions of thousands of galaxies. When the data was plotted on a graph showing galaxy distance and direction, scientists noticed something peculiar. The galaxies appeared to form thin arcs and walls rather than filling the map evenly. One of the most famous discoveries from these early surveys was a structure called the Great Wall. The name might sound dramatic, but it was actually quite accurate. The Great Wall is a vast sheet of galaxies stretching across roughly 500 million light-years. It's one of the largest known structures in the universe, and it was only the beginning. As surveys expanded, astronomers uncovered more and more enormous structures. Filaments connecting clusters, walls stretching across cosmic distances, voids so large that entire regions of space appeared nearly empty. With each new data set, the pattern became clearer. The universe was not a random scatter of galaxies, it was organised. Not in the sense that someone arranged it deliberately, but in the sense that gravity and the laws of physics naturally produce patterns on the largest possible scales. And once scientists realised this, a new question emerged. What created the cosmic web? How did the universe develop such an enormous and intricate structure? The answer begins very early in the history of the cosmos, not long after the Big Bang. In the beginning, the universe was remarkably uniform. Matter and energy were distributed almost evenly throughout space, with only tiny fluctuations in density. These fluctuations were incredibly small. In fact, when scientists measure the early universe using the cosmic microwave background radiation, the variations in density are only about 1 part in 100,000. Yet those tiny differences were enough. Over billions of years, gravity slowly amplified them. Regions that were slightly denser than average attracted more matter. As more matter gathered, gravity became stronger, pulling in even more material. Meanwhile, less dense regions lost matter to their surroundings. Gradually, over immense stretches of time, these small variations grew into the structures we see today. Galaxies formed where matter collected. Clusters formed where many galaxies gathered together. Filaments appeared as matter flowed along gravitational pathways connecting dense regions. And the vast voids formed in areas where matter gradually drained away. The cosmic web emerged not from chaos, but from the steady and patient pull of gravity acting over billions of years. Interestingly, much of the structure of the cosmic web is shaped by something we cannot see directly: dark matter. Dark matter does not emit light, reflect light, or absorb light in ways we can easily detect, yet it exerts gravity. In fact, dark matter makes up most of the matter in the universe. Scientists believe that dark matter formed the original skeleton of the cosmic web. Ordinary matter, the kind that forms stars, planets, and galaxies, gathered along these invisible dark matter filaments. Over time, galaxies formed within these structures, lighting up the web like tiny lanterns, outlining an otherwise invisible framework. So when astronomers map the cosmic web today, they're actually tracing the distribution of galaxies that formed along dark matter filaments. In a sense, we are seeing only the illuminated version of a much larger invisible structure, and that raises an intriguing thought. The cosmic web we observe may only be a partial view of the full structure of the universe. There could be even more complexity hidden within the dark matter network that we have not yet fully mapped. Even so, the cosmic web remains one of the most extraordinary discoveries in modern astronomy. It reveals that the universe, on its largest scales, has a structure that connects galaxies across unimaginable distances. And perhaps even more remarkable, it places our own galaxy within that vast network. Right now, as Earth spins quietly and the night sky stretches overhead, the Milky Way sits within one of those cosmic filaments. Our galaxy is not alone, not isolated, but part of a much larger structure stretching across the universe. And the more astronomers study this web, the more questions appear. Just how large is the cosmic web, really? How far do its filaments stretch? And what lies beyond the parts of it we can observe? At first glance, the universe looks wonderfully chaotic. If you step outside on a clear night and look up at the sky, the stars appear scattered across the darkness in no particular order. Some shine brighter than others, some cluster loosely together, but overall the pattern seems random. It feels as though someone tossed a handful of glitter across a black sheet and simply left it there. For most of human history, that impression shaped how people imagined the universe. The stars appeared randomly distributed, and when telescopes began revealing distant galaxies in the early 20th century, the assumption naturally continued. Galaxies, it seemed, must also be scattered somewhat randomly through space. After all, when astronomers first began discovering galaxies beyond the Milky Way, they were mostly studying them one at a time. A galaxy here, another one there, a small cluster perhaps. But nothing that obviously suggested a vast hidden structure tying everything together. And to be fair, the universe is so unimaginably large that spotting patterns within it is not easy. Imagine standing in the middle of a desert with only a small flashlight. The sand stretches in every direction for hundreds of kilometers, but your flashlight only illuminates a few meters ahead of you. You might notice ripples in the sand nearby, perhaps a small dune or two, but the grand patterns of the desert remain invisible. Early astronomers were in a similar situation. Their telescopes allowed them to see galaxies far beyond the Milky Way, but they could only observe small pieces of the universe at a time. The larger pattern, if there was one, remained hidden simply because there was not yet enough data to reveal it. Still, small clues began appearing. In the 1920s and 1930s, astronomers were already aware that galaxies sometimes gathered in groups. One of the most famous early discoveries came from the Swiss astronomer Fritz Zwicky, who studied a massive collection of galaxies known as the Coma Cluster. The Coma Cluster contains more than 1,000 galaxies bound together by gravity. Even by cosmic standards, it is a large and impressive structure. But when Zwicky studied how fast the galaxies inside the cluster were moving, he noticed something puzzling. The galaxies were moving far too quickly to be held together by the visible matter alone. If gravity from the galaxies themselves were the only force at work, the cluster should have flown apart long ago. To explain the motion, Zwicky proposed that there must be additional unseen matter, providing extra gravity. Today, we call that mysterious substance dark matter, but at the time the idea was met with skepticism. The concept of invisible matter sounded strange, even a little uncomfortable, and many scientists preferred to set the problem aside for later. Yet Zwicky's observations quietly planted an important seed. If galaxies could gather into massive clusters held together by gravity, then perhaps the universe contained structures far larger than individual galaxies. Other astronomers soon noticed similar patterns. In the decades that followed, more galaxy clusters were discovered. Some were relatively small, containing only dozens of galaxies. Others, like the Coma Cluster, were enormous cosmic cities containing thousands. But even more intriguing was the realization that clusters themselves sometimes appeared close together. Groups of clusters seemed to form loose associations that astronomers began calling superclusters. One of the most famous examples is the Virgo supercluster, the enormous region of space that contains our own Milky Way galaxy. The Virgo supercluster stretches across more than 100 million light-years and includes thousands of galaxies spread across many clusters and groups. When scientists first mapped this region, it was tempting to imagine the universe as a collection of these massive island-like superclusters scattered through space. Still, the assumption remained that, on the largest scales, everything would eventually average out into something roughly uniform. That expectation came from an idea called the cosmological principle. The cosmological principle is a foundational assumption in modern cosmology. It states that when viewed on very large scales, the universe should appear the same everywhere and in every direction. In other words, no particular region of the universe should be special. This idea was supported by many observations. When astronomers looked far enough into space, galaxies appeared in every direction. The cosmic microwave background radiation, a faint glow left over from the early universe, also appeared nearly uniform across the sky. So even though galaxies sometimes formed clusters and superclusters, scientists believed that if you zoomed out far enough, the universe would still look fairly smooth. But science has a habit of revealing surprises when people start measuring things carefully. During the mid-20th century, astronomers began conducting more systematic surveys of galaxies. Instead of observing a few galaxies at a time, they attempted to catalogue large numbers of them across wide regions of the sky. This task was not easy. Before digital cameras and powerful computers, astronomers relied on photographic plates to record images of the night sky. Each plate captured thousands of faint galaxies, tiny smudges of light that had to be carefully measured and catalogued by hand. The work was slow and painstaking, but slowly the data began to accumulate. One of the first hints that something unusual was happening came from a simple observation. Galaxies did not appear evenly spaced. Some areas of the sky contained many galaxies close together, while other areas seemed strangely empty. At first, scientists wondered if this uneven distribution might simply be the result of observational bias. Perhaps some regions of the sky were easier to observe, or perhaps dust within our own galaxy was blocking the view in certain directions. But as more observations were collected, the pattern persisted. Certain regions truly did contain more galaxies than others. Then something even more interesting began to emerge. Galaxies seemed to form long chains. When astronomers plotted the positions of galaxies on maps, they noticed that galaxies often appeared aligned in elongated structures rather than random clusters. Picture a handful of beads scattered across a table. If the beads land randomly, they will form no particular pattern, but if they land along thin threads stretched across the table, you would see clear lines connecting them. That was roughly what astronomers were beginning to see in their galaxy maps. At first, these alignments were subtle. The number of galaxies mapped at the time was still relatively small, so the patterns were not yet obvious. But a few astronomers began to suspect that the universe might contain much larger structures than anyone had previously imagined. One of the pioneers in this area was the American astronomer George Abel. In the 1950s, Abel compiled one of the first comprehensive catalogues of galaxy clusters. He carefully examined photographic plates from the Palomar Observatory Sky Survey and identified thousands of clusters across the sky. Abel's catalogue became a foundational tool for studying large-scale cosmic structure. When astronomers analysed the positions of these clusters, they noticed something intriguing. Clusters were not randomly scattered either. They often appeared close to one another, forming enormous groupings across vast regions of space. These groupings hinted that the universe might contain structures even larger than superclusters. Still, without precise distance measurements, it was difficult to confirm the true three-dimensional arrangement of galaxies. Looking at galaxies on the sky is a bit like looking at a city skyline from far away. Buildings may appear close together from your perspective, but they could actually be separated by large distances along your line of sight. To truly map the universe, astronomers needed a way to measure how far away each galaxy was. Fortunately, they had a tool for that. It's called redshift. When galaxies move away from us, the light they emit becomes stretched to longer wavelengths. This shift toward the red end of the spectrum is known as redshift, and it provides a way to estimate a galaxy's distance. The farther away a galaxy is, the faster it appears to be moving away due to the expansion of the universe and the larger its redshift. By measuring redshift, astronomers could determine not only where a galaxy appeared on the sky, but also how far away it was. This allowed them to construct three-dimensional maps of the universe. Once these maps began to take shape, the universe started revealing its deeper structure. Instead of a smooth distribution of galaxies, scientists began seeing enormous patterns, clusters linked together. Superclusters extended across immense distances, and galaxies appeared to trace long filaments through space. One particularly important moment came in the late 1970s, when astronomers Margaret Geller and John Huckra began mapping galaxies using data from the CFA Redshift survey. They plotted galaxy positions on a graph showing distance versus direction in space. What appeared on that graph surprised everyone. Instead of a random scatter of points, the galaxies formed curved arcs and thin walls surrounding large empty regions. The structure resembled a sponge or foam, or perhaps more fittingly a web. At the time, this was one of the clearest indications that the universe possessed a complex large-scale structure. Galaxies were not simply sprinkled randomly through space. They were arranged along enormous patterns stretching across hundreds of millions of light years. Between those patterns were vast cosmic voids, regions where very few galaxies existed at all. It was the first clear hint that the universe might be organized on scales far larger than anyone had previously imagined. And yet, even this discovery was only the beginning. Because as galaxy surveys grew larger and more detailed, astronomers began to uncover structures even more immense than those early maps suggested. Walls of galaxies stretching across 500 million light years. Filaments connecting clusters across cosmic distances. Voids so large that entire regions of the universe seemed almost empty. Piece by piece, a picture was forming. The The universe was not random. It was woven together. Long before astronomers could see the grand architecture of the universe, they faced a very simple problem. They did not yet have a map. For most of human history, people had maps of the Earth, maps of the sky, and eventually maps of our own galaxy. But the universe beyond the Milky Way remained largely uncharted territory. Astronomers could point telescopes at distant galaxies, study their light, and measure their motion, yet they still lacked something crucial. They did not know how those galaxies were arranged across the enormous expanse of space. In other words, scientists could see many individual pieces of the cosmic puzzle, but no one had yet laid them out on a table to see the bigger picture. Creating such a map is not as simple as it might sound. When you look at the night sky, everything appears painted onto the inside of a dome. The stars, planets, and galaxies all seem to sit on the same flat surface, even though in reality they are separated by vast distances. Imagine standing on a hill overlooking a city at night. The lights from buildings and streets blend together into a single glowing pattern, and it can be difficult to judge how far away each light actually is. Some lights might belong to buildings right in front of you, while others come from towers kilometers away. Astronomers faced a similar challenge when looking at galaxies. They could see where galaxies appeared on the sky, but that alone did not reveal their true positions in three-dimensional space. To build a proper map of the universe, scientists needed two pieces of information for every galaxy they observed. First, they needed to know where the galaxy appeared on the sky. Second, they needed to know how far away it was. Once both of those measurements were available, astronomers could begin constructing a three-dimensional map of the cosmos. The first part of that process was relatively straightforward. Telescopes could easily determine a galaxy's position on the sky using celestial coordinates, much like latitude and longitude on Earth. The real challenge was measuring distance. Galaxies are incredibly far away, and traditional methods used to measure nearby stars simply did not work at such enormous scales. Astronomers needed a different approach. Fortunately, the universe provided one. Earlier in the 20th century, the astronomer Edwin Hubble discovered something remarkable about distant galaxies. When he studied their light using a spectroscope, he found that most galaxies appeared to be moving away from us. More specifically, the light from those galaxies was shifted toward the red end of the spectrum. This effect is known as redshift. Redshift occurs because the universe itself is expanding. As space stretches, the light travelling through it also stretches, increasing its wavelength and shifting it toward redder colours. Hubble noticed that the farther away a galaxy appeared to be, the greater its redshift. From this observation, scientists developed a relationship known as Hubble's law. Simply put, the farther away a galaxy is, the faster it appears to be moving away from us. That relationship allowed astronomers to estimate the distance to a galaxy by measuring its redshift. Suddenly, the second piece of the cosmic map became possible. By measuring redshift, scientists could determine how far away galaxies were, giving them the depth needed to transform flat sky observations into true three-dimensional maps. At first, the number of galaxies with measured redshifts was very small. Each measurement required careful observation with large telescopes, and the process was time-consuming. Astronomers had to collect enough light from a galaxy to analyse its spectrum and determine how much its light had shifted. Early studies involved dozens of galaxies, then hundreds. Gradually, as telescopes improved and instruments became more precise, astronomers began measuring redshifts for thousands of galaxies. This opened the door to something entirely new. Instead of simply cataloguing galaxies, scientists could begin mapping the structure of the universe itself. One of the earliest major efforts in this direction came from the Harvard Smithsonian Center for Astrophysics during the 1970s. Astronomers Margaret Geller and John Ushra led a project that would become known as the CFA Redshift Survey. Their goal was ambitious but straightforward. They wanted to measure the redshifts of as many galaxies as possible within a certain region of the sky, and use that information to create a three-dimensional map of the nearby universe. The process required patience. Each galaxy had to be observed individually, its light carefully captured and analysed to determine its redshift. The data was then plotted on a graph representing its position in space. As more galaxies were added to the map, the structure of the universe slowly began to reveal itself. At first, the points representing galaxies appeared somewhat scattered, but as the map grew larger, patterns started to emerge. Galaxies did not fill space evenly. Instead, they seemed to trace thin arcs and long walls across the map. Between those structures were enormous empty regions where almost no galaxies appeared at all. When Geller and Hukra examined their maps, they noticed that galaxies often formed curved sheets surrounding vast voids. The pattern resembled bubbles in foam or the cells in a sponge. It was a striking discovery. The universe, it seemed, was not random. Galaxies were arranged in enormous structures stretching across hundreds of millions of light years. One of the most famous discoveries from these early surveys was something called the Great Wall. Despite the name, the Great Wall is not a solid structure in the way we might imagine a wall on Earth. Instead, it is a massive sheet of galaxies forming a thin layer within the cosmic web. The Great Wall stretches roughly 500 million light-years across, making it one of the largest known structures in the universe. To grasp how large that is, consider that our entire Milky Way galaxy spans about 100,000 light-years. The Great Wall is about 5,000 times larger. Discoveries like this forced astronomers to rethink their understanding of cosmic structure. Until then, many scientists had assumed that while galaxies might form clusters and superclusters, the universe would eventually smooth out when viewed on sufficiently large scales. But these surveys revealed structures far larger than expected. Walls, filaments, and vast voids appeared again and again in the data, and with every new map the same pattern repeated itself. The universe looked like a network, yet the CFA survey was only the beginning. As technology improved, astronomers began launching even more ambitious projects. One of the most influential of these was the Sloan Digital Sky Survey, often abbreviated as SDSS. Unlike earlier surveys that relied on photographic plates, SDSS used advanced digital detectors capable of capturing enormous amounts of data. The telescope dedicated to this project was located at Apache Point Observatory in New Mexico. Beginning in the early 2000s, the survey began mapping millions of galaxies across a large portion of the sky. For each galaxy, scientists measured its position and redshift, building an extraordinarily detailed map of the universe. When these data were visualized, the cosmic web appeared more clearly than ever before. Galaxies traced long filaments connecting dense clusters. At the intersections of these filaments sat massive galaxy clusters, containing hundreds or thousands of galaxies. Between the filaments stretched enormous cosmic voids, some spanning hundreds of millions of light-years. The Sloan Digital Sky Survey transformed our understanding of cosmic structure. It showed that the web-like arrangement hinted at by earlier surveys extended across enormous regions of space. The universe, when viewed on large scales, truly resembled a vast network of interconnected filaments. Even more impressive was the scale of the maps being produced. Astronomers were no longer mapping just a few thousand galaxies, they were mapping millions. With modern instruments and automated analysis techniques, researchers could now study patterns across billions of light-years. And yet, even with these incredible advances, astronomers were still only seeing part of the universe. The observable universe, the region of space whose light has had time to reach us since the Big Bang, stretches about 93 billion light-years across. Even the largest galaxy surveys map only a fraction of that enormous volume. Still, each new survey reveals more detail about the cosmic web. Filaments appear in ever greater clarity. Voids become easier to identify. Clusters of galaxies stand out as glowing nodes where many filaments intersect. In recent years, astronomers have even begun mapping the faint gas that flows between galaxies along these filaments. This gas, known as the intergalactic medium, forms part of the same cosmic structure that guides galaxy formation. It is extremely diffuse, often only a few atoms per cubic meter, yet it fills vast regions of space and traces the underlying framework of the universe. Observing this gas requires incredibly sensitive instruments, but when scientists manage to detect it, the cosmic web becomes even more apparent. What once looked like isolated galaxies now appears as a connected system stretching across unimaginable distances. Looking at these maps can feel a bit like examining a city from an airplane at night. Clusters of lights mark dense neighbourhoods. Long highways connect those neighbourhoods together, and between them lie darker regions where fewer lights appear. Except in this case, the city spans billions of light years and contains trillions of galaxies. Mapping the universe has become one of the great scientific achievements of modern astronomy. Each new survey adds detail to our understanding of the cosmic web, revealing how galaxies are arranged on the larger scales. But these maps also raise deeper questions. If galaxies trace the filaments of this vast network, what exactly forms the skeleton underneath? Why did matter gather into strands instead of spreading evenly across space? And how did these enormous structures form in the first place? For a long time, astronomers suspected that galaxies might follow patterns. Clusters had been observed, superclusters had been catalogued, and early surveys hinted that galaxies were not scattered perfectly evenly across space. Still, hints and suspicions are not the same as a clear picture. Scientists needed something unmistakable, a moment when the structure of the universe could be seen directly rather than inferred. That moment arrived gradually, but when it did, the result was striking enough that many astronomers still remember the first time they saw the images. It happened when galaxy maps became large enough to show the universe in slices. Earlier observations had plotted galaxies across the sky, but those maps were limited because they lacked depth. Without distance information, everything appeared compressed onto a flat surface. Galaxies that were millions or billions of light years apart could appear right next to one another. Once redshift measurements began providing reliable distances, astronomers could finally place galaxies into three-dimensional space. To visualize this information, researchers created what are sometimes called wedge diagrams. Imagine taking a thin slice of the universe, almost like cutting a wedge out of a pie. Along the bottom of the wedge lies the Earth, the point from which observations are made. As you move outward along the wedge, you travel farther into space. Each dot plotted inside the wedge represents a galaxy. The farther away the galaxy is, the farther out it appears on the diagram. When the first of these maps began to fill with data, astronomers expected something fairly ordinary. They assumed the dots would scatter somewhat evenly across the wedge, perhaps clustering in places but otherwise forming a loose cloud of galaxies. Instead, something entirely different appeared. The dots began forming arcs, not just small clusters, but enormous sweeping curves stretching across the diagram. Galaxies lined up along thin structures that resembled the edges of bubbles or the walls of gigantic cells. Between these arcs were enormous gaps where very few galaxies appeared at all. When scientists stepped back and looked at the pattern, it was unmistakable. The universe was not evenly filled with galaxies. Instead, galaxies were arranged along immense structures that surrounded vast empty regions. One of the first clear demonstrations of this pattern came from the CFA redshift survey during the late 1970s and early 1980s. Margaret Geller and John Huchra had spent years collecting redshift measurements for galaxies across a large region of the sky. Each new measurement added another point to the map. At first the pattern was unclear, but as the number of galaxies increased, the shape of the structure emerged more clearly. One of the most famous images from the survey is often called the slice of the universe. In this image, galaxies form thin curved walls surrounding large voids. The resemblance to a sponge or foam is almost impossible to ignore. Clusters appear where multiple walls intersect, forming dense knots of galaxies. Filaments stretch between these clusters like threads connecting beads, and the voids between them form enormous cavities spanning tens or even hundreds of millions of light years. For many astronomers, seeing this structure for the first time was a moment of quiet astonishment. The universe had revealed a hidden architecture. Up until that point, the large-scale structure of the cosmos had been mostly theoretical. Scientists suspected gravity might create patterns over time, but no one had clearly seen the full structure laid out before them. Now it was visible. The universe looked like a web. That realization did not arrive all at once. At first, astronomers cautiously referred to walls, filaments, and voids without fully committing to the idea of a universal network. Scientists tend to be careful when introducing new concepts, especially when the evidence is still growing. But as more data arrived, the same pattern kept appearing. Independent surveys began confirming the structure. Wherever astronomers looked with sufficient data, they found the same thing. Galaxies formed long filaments, clusters gathered at intersections, vast empty regions stretched between them. The cosmic web was not a coincidence. It was the fundamental large-scale structure of the universe. One of the most dramatic discoveries during this period was the identification of an enormous structure known as the Great Wall. The Great Wall was discovered in 1989 by Margaret Geller and John Huchra while analysing data from the Galaxies survey. This structure stretches roughly 500 million light-years across. To put that into perspective, the Milky Way galaxy is about 100,000 light-years in diameter. The Great Wall is therefore roughly 5,000 times larger than our entire galaxy. At the time of its discovery, it was the largest known structure in the universe, and it was not alone. Over the following decades, astronomers discovered additional enormous structures. The Sloan Great Wall, identified in data from the Sloan Digital Sky Survey, stretches nearly 1.4 billion light-years. Other massive structures include the Hercules Corona Borealis Great Wall and the Boss Great Wall, each composed of countless galaxies arranged in enormous filaments and sheets. These discoveries made something very clear. The universe contains structures far larger than anyone had once imagined. Yet these immense walls and filaments are not isolated objects. They are simply parts of a much larger pattern. When astronomers combine data from different regions of the sky, the structures begin connecting together. Filaments link clusters to clusters, walls curve around enormous voids, and together they form a vast three-dimensional network. This network spans the entire observable universe. That realization changed how scientists think about cosmic structure. Instead of imagining galaxies as separate islands scattered through space, astronomers began thinking of them as light strung along enormous cosmic highways. Galaxies form where matter flows along filaments. Clusters appear where multiple filaments intersect. And the largest empty regions emerge where matter has gradually drained away over billions of years. The cosmic web provides the scaffolding upon which the visible universe is built. Yet the most fascinating part of this discovery may be how subtle the structure actually is. If you zoom into a small region of space, the web is not immediately obvious. Galaxies appear, scattered somewhat randomly at smaller scales. It is only when you zoom out far enough that the pattern begins to reveal itself. This is somewhat similar to looking at a forest. If you stand among the trees, you mostly see trunks, branches, and leaves. The arrangement may seem irregular, but if you climb high enough above the forest, patterns emerge. You might see rivers winding through the landscape, hills shaping the growth of trees, or clearings spreading across large regions. The cosmic web works in much the same way. Its structure becomes visible only when you examine enormous volumes of space. Another interesting aspect of the cosmic web is how empty the voids between filaments truly are. Cosmic voids can stretch across hundreds of millions of light-years. Within these regions, galaxies are extremely rare. Some voids contain only a few small galaxies drifting in relative isolation. Others are nearly empty. Compared to the dense clusters along the filaments, these voids contain very little matter. Yet they play an important role in shaping the universe. Gravity gradually pulls matter away from the voids toward denser regions. Over billions of years, this process sharpens the structure of the cosmic web, making filaments denser and voids emptier. In a sense, the cosmic web is constantly evolving. Matter flows slowly along its filaments. Clusters grow larger as galaxies merge. Voids expand as surrounding matter moves away. All of this happens over timescales so vast that the changes are almost imperceptible from a human perspective. Yet across billions of years, the structure of the universe slowly becomes more defined. Another fascinating discovery emerged as astronomers began comparing these observations with computer simulations. By modelling the early universe and allowing gravity to shape matter over time, scientists could simulate the growth of cosmic structure. When they ran these simulations, something remarkable happened. The simulated universe formed filaments and voids almost identical to those observed in real galaxy surveys. The cosmic web appeared naturally from the laws of physics. Tiny density fluctuations in the early universe gradually grew under gravity, forming the enormous network of structures we observe today. This was a powerful confirmation that the basic understanding of cosmic evolution was on the right track. The universe, starting from nearly uniform conditions after the Big Bang, could naturally develop the intricate web-like structure seen in galaxy maps. Perhaps the most humbling aspect of this discovery is our own place within the web. The Milky Way galaxy resides inside a filament of the cosmic web. Our local group of galaxies lies within a larger structure called the Linear-Kea supercluster. This supercluster itself forms part of the larger cosmic web, stretching across the observable universe. In other words, our galaxy is not drifting through space alone. It is part of an immense network connecting billions of galaxies across billions of light years. Once astronomers realized that the universe forms a vast network rather than a random scatter of galaxies, a natural question followed. What does this structure actually look like? Not in the sense of an artist's impression or a colourful simulation, but in terms of its real physical layout. If you could somehow step far outside the Milky Way, travel millions or even billions of light years away, and look back at the universe from a distance, what shape would you see? The answer is both elegant and surprisingly simple. The cosmic web is made of four main features: filaments, clusters, walls, and voids. These elements repeat again and again across the observable universe, forming the enormous structure astronomers now study in detail. It helps to imagine the cosmic web not as a flat web like the one a spider spins between branches, but as a three-dimensional network extending in every direction through space. The strands are not lines drawn on a page, they are enormous rivers of galaxies stretching across unimaginable distances. Let's begin with the most visible part of the web, the filaments. Cosmic filaments are long, thin structures made of galaxies, gas, and dark matter. They can stretch for hundreds of millions of light years, sometimes even longer. Inside these filaments, galaxies are not packed tightly together. Instead, they are spaced along the filament like towns scattered along a highway. Each galaxy contains billions of stars, but the distances between galaxies remain enormous. Even within these cosmic strands, most of the volume is empty space. Still, compared with the surrounding regions, filaments contain a much higher concentration of matter. If you were somehow able to travel along one of these filaments, you would pass from galaxy group to galaxy group, occasionally encountering clusters where the density increases dramatically. Clusters are the next major feature of the cosmic web. Where several filaments intersect, gravity pulls large amounts of matter together, forming galaxy clusters. These clusters are among the most massive objects in the universe. A typical galaxy cluster may contain hundreds or even thousands of galaxies bound together by gravity. In addition to the galaxies themselves, clusters also contain enormous amounts of hot gas and dark matter. In fact, most of the mass inside a cluster is not in stars or galaxies at all. The majority exists as dark matter, an invisible substance that reveals itself only through its gravitational influence. clusters act as the nodes of the cosmic web. They are the intersections where multiple filaments meet, creating dense hubs within the larger network. If the cosmic web were compared to a transportation system, clusters would be the major cities where many highways converge. Between those hubs stretch the long filaments that guide the flow of matter across the universe. Another important feature of the web is something astronomers sometimes call walls or sheets. Walls are enormous structures made of galaxies arranged in broad, thin layers. Instead of forming narrow strands like filaments, walls resemble vast surfaces stretching across space. One of the most famous examples is the Great Wall, discovered during the CFA redshift survey. This structure stretches roughly 500 million light-years across, making it one of the largest known formations in the universe. To imagine a wall, picture a cluster of soap bubbles packed together. Where the bubbles press against each other, thin surfaces form between them. Those surfaces are somewhat similar to the walls of galaxies observed in large-scale cosmic maps. They are not solid barriers, of course. They are simply regions where galaxies happen to be concentrated along extended planes. Between the filaments, clusters, and walls lie perhaps the most mysterious parts of the cosmic web. These are the voids. Cosmic voids are enormous regions containing very few galaxies. Some voids stretch across hundreds of millions of light-years. Within them, galaxies are extremely rare, sometimes separated by distances far greater than those found in more crowded regions. From a cosmic perspective, voids make up most of the volume of the universe. The filaments and clusters may contain the majority of the galaxies, but the voids occupy the vast spaces between them. If you could visualize the universe from afar, the voids would appear as enormous cavities surrounded by thin, glowing threads of galaxies. This is why astronomers often compare the cosmic web to foam or sponge. In a piece of foam, most of the space exists inside the bubbles. The material itself forms thin surfaces surrounding those empty pockets. The cosmic web follows a similar pattern. Matter gathers along thin structures while enormous empty regions fill the space between them. But even the voids are not completely empty. Although galaxies are scarce inside voids, they still contain faint gas and dark matter spread thinly throughout the region. This material is so diffuse that detecting it requires extremely sensitive instruments, yet its presence confirms that voids are not truly empty. They are simply regions where matter density is very low compared with the surrounding structures. Another fascinating aspect of the cosmic web is its scale. The structures we are describing span distances so large that ordinary human intuition struggles to grasp them. A single filament may stretch for hundreds of millions of light-years. Walls of galaxies can extend even farther. Clusters contain masses equivalent to thousands of galaxies. Yet even these enormous features are only pieces of a larger pattern. When astronomers combine data from galaxy surveys covering vast regions of the sky, the cosmic web appears to extend across the entire observable universe. Everywhere scientists look, they see the same basic structure repeated. Filaments, clusters, walls, voids. Again and again, the same architecture emerges. It is almost as if the universe follows a consistent design principle on its larger scales. Interestingly, this structure is not unique to the visible matter we can observe. Computer simulations of the universe also produce similar patterns. When scientists simulate the evolution of matter under gravity, starting from tiny fluctuations in the early universe, the resulting structures naturally form filaments and clusters connected in a web-like network. These simulations often show dark matter forming the initial skeleton of the cosmic web. As time passes, ordinary matter flows into the gravitational wells created by dark matter, eventually forming galaxies along those same filaments. The galaxies we observe therefore act as tracers, revealing the locations of much larger structures made primarily of dark matter. This idea helps explain why the cosmic web appears so consistent across different regions of space. The underlying physics of gravity and cosmic expansion naturally leads to the formation of these patterns. Over billions of years, matter slowly migrates toward denser regions, leaving behind expanding voids and growing filaments. In other words, the cosmic web is not something that was deliberately arranged. It emerged from the natural evolution of the universe. Another interesting detail is that the cosmic web is constantly changing, although the changes occur extremely slowly. Galaxies move along filaments under the influence of gravity. Clusters gradually grow as they attract surrounding matter. Voids expand as nearby material flows outward toward denser regions. These processes unfold over billions of years, far longer than any human timescale. Still, simulations allow scientists to watch these changes unfold in accelerated form. When researchers run models of cosmic evolution on powerful supercomputers, they can see the web gradually forming from the early universe. Tiny density fluctuations slowly grow into long filaments. Clusters appear at intersections. Voids expand between them. By the time billions of years have passed in the simulation, the resulting structure closely resembles the cosmic web we observe today. There is another way to think about the appearance of the cosmic web. Instead of imagining it as a web of threads, some scientists describe it as a network of rivers. Matter flows slowly along these cosmic rivers under the pull of gravity. Gas and dark matter drift along filaments toward the dense intersections where galaxy clusters reside. Over time, galaxies themselves migrate through this network, following the gravitational pathways laid out by the web. From this perspective, the cosmic web becomes less like a static structure and more like a dynamic system. Matter moves along its strands. Clusters grow where the flows converge. Voids expand as surrounding regions lose material. The universe, on its larger scales, behaves like a vast system of interconnected streams. When astronomers first began mapping the cosmic web, the glowing galaxies seemed to outline its structure beautifully. Filaments stretched across the maps, clusters formed bright intersections, and enormous voids appeared between them. It was tempting to imagine that the galaxies themselves were responsible for shaping this vast architecture. But the deeper scientists looked, the more they realized something important. The galaxies alone could not account for the structure they were seeing. There simply was not enough visible matter in the universe to produce the gravitational forces required to build such enormous formations. If the universe contained only stars, gas, dust, and planets, gravity would be far too weak to pull matter together into the massive filaments and clusters observed across billions of light years. Something else had to be involved. Something invisible. This mysterious ingredient is known today as dark matter. The name sounds dramatic, almost like something invented for a science fiction story. Yet the concept emerged from careful observation rather than imagination. Astronomers did not set out looking for dark matter. Instead, they stumbled upon it when the numbers simply refused to make sense. The first hints appeared in the early 20th century when scientists began studying how galaxies move. If you observe a collection of objects held together by gravity, such as planets orbiting the Sun, you can estimate the amount of mass present by measuring how fast those objects move. Faster motion requires stronger gravitational pull, and stronger gravity requires more mass. Astronomers applied this same reasoning to galaxy clusters. One of the earliest researchers to notice something strange was Fritz Zwicky in the 1930s. While studying the Coma cluster, Zwicky measured how quickly galaxies inside the cluster were moving relative to one another. The result was puzzling. The galaxies were moving far too fast. Based on the visible mass of the cluster, meaning the mass contained in stars and gas, the gravitational pull should not have been strong enough to hold the cluster together. The galaxies should have escaped long ago, drifting apart into space, yet the cluster remained intact. Zwicky concluded that there must be additional mass present, something invisible that could not be detected through ordinary telescopes. He called this missing substance Dunkle Materie, which translates from German as dark matter. At the time, many scientists were skeptical. The idea that the universe might contain vast amounts of unseen matter seemed rather extreme. Observational evidence was limited, and it was difficult to imagine what such matter might be made of. For several decades, the concept remained controversial. Then, in the 1970s, a new set of observations provided much stronger evidence. Astronomers Vera Rubin and Kent Ford began studying how stars move inside spiral galaxies. They measured the rotation speeds of stars at different distances from the centres of galaxies, expecting to see a pattern similar to what occurs in our solar system. In the solar system, planets closer to the Sun orbit more quickly than those farther away. Mercury moves rapidly around the Sun, while Neptune travels much more slowly along its distant orbit. This pattern occurs because most of the mass of the solar system is concentrated in the Sun. Astronomers expected something similar in galaxies. Most of a galaxy's visible mass is concentrated near its centre, where the majority of stars reside. If only visible matter were present, stars near the outer edges of galaxies should orbit more slowly than stars near the centre. But that is not what Rubin observed. Instead, the rotation speeds of stars remained almost constant even far from the galactic centre. Stars at the outer edges of galaxies were moving just as fast as those much closer in. This result implied that galaxies contained far more mass than what could be seen. The extra mass appeared to surround each galaxy in a large invisible halo, extending well beyond the visible stars. This halo, scientists concluded, must consist of dark matter. Once astronomers began accounting for dark matter, many puzzling observations suddenly made sense. Galaxy clusters could remain gravitationally bound. Galaxies could rotate as observed. And perhaps most importantly for our story, the formation of the cosmic web became far easier to explain. Dark matter appears to dominate the mass of the universe. Ordinary matter, the atoms that form stars, planets, and people, makes up only a small fraction of the total cosmic mass. Most of the matter in the universe exists in this invisible form. Although dark matter does not interact with light, it still interacts through gravity, and gravity over billions of years shapes the structure of the universe. To understand how dark matter builds the cosmic web, it helps to go back to the early universe. Shortly after the Big Bang, the universe was extremely hot and dense. Matter and radiation filled space in an almost uniform mixture, with only tiny fluctuations in density. These fluctuations were incredibly small, roughly 1 part in 100,000. Yet those tiny differences mattered. Regions that were slightly denser than average contained a bit more mass. Gravity caused those regions to attract surrounding material, gradually growing larger over time. Dark matter played a crucial role during this process. Unlike ordinary matter, dark matter did not interact strongly with radiation. That meant it could begin clumping together earlier in the universe's history. While normal matter remained mixed with radiation in the early cosmic plasma, dark matter quietly formed the first gravitational structures. These early dark matter clumps gradually merged and stretched under gravity, forming long filaments and dense nodes. In other words, dark matter began constructing the skeleton of the cosmic web long before galaxies existed. As the universe cooled and ordinary matter began forming atoms, gas slowly fell into the gravitational wells created by dark matter. Where dark matter filaments existed, gas accumulated. Where gas accumulated, galaxies eventually formed. The galaxies we observe today are therefore not the architects of the cosmic web. They are more like lights decorating a much larger invisible framework. If we could somehow see dark matter directly, the universe might look even more intricate than the galaxy maps currently reveal. Simulations provide a glimpse of what that hidden structure might look like. Using powerful supercomputers, scientists model the evolution of dark matter in the expanding universe. Starting with tiny fluctuations in density shortly after the Big Bang, the simulations allow gravity to shape the distribution of matter over billions of years. The results are remarkable. Dark matter forms long filaments stretching across space. Dense nodes appear where filaments intersect. Between them lie vast regions of extremely low density. When scientists overlay galaxies onto these simulated dark matter maps, the galaxies appear precisely along the filaments. matching observations of the real universe. In other words, the cosmic web emerges naturally when dark matter is included in the equations. Without dark matter, the simulations fail to reproduce the structures astronomers observe. With it, the large-scale architecture of the universe appears almost exactly as seen in galaxy surveys. Even though dark matter cannot be observed directly, scientists have developed several ways to detect its presence indirectly. One method involves gravitational lensing. According to Einstein's theory of general relativity, massive objects can bend the path of light travelling near them. When light from distant galaxies passes through a region containing large amounts of mass, its path becomes slightly distorted. By carefully measuring these distortions, astronomers can map the distribution of mass in the universe, including dark matter. When researchers use gravitational lensing to map cosmic structures, they find that dark matter traces the same filaments revealed by galaxy surveys. The galaxies outline the web, but the underlying mass distribution shows that dark matter forms the bulk of the structure. Another fascinating aspect of dark matter is that, despite its enormous influence, scientists still do not know exactly what it is. Various theories propose different possibilities. Some researchers suggest that dark matter might consist of previously unknown particles that interact only weakly with ordinary matter. Others propose more exotic possibilities, including particles that formed during the earliest moments of the universe. Experiments around the world are currently searching for these particles, using detectors buried deep underground or sensitive instruments placed in space. So far, none of these experiments has produced a definitive answer. Dark matter remains one of the greatest mysteries in modern physics, yet even without knowing its precise nature, astronomers can see its effects everywhere. It shapes the rotation of galaxies, it binds galaxy clusters together, and most importantly for our story, it provides the gravitational framework that allows the cosmic web to form. Without dark matter, the universe would look very different. Galaxies might still exist, but the vast network of filaments and clusters spanning billions of light years might never have emerged. Instead of a web, the universe might resemble a far more uniform and less structured expanse. In a quiet way, dark matter acts like an invisible architect. It lays down the scaffolding of the cosmos, guiding the flow of matter across unimaginable distances. Galaxies illuminate that scaffolding, revealing just enough of the structure for us to glimpse the pattern. Yet the true framework remains largely hidden, and this invisible architecture raises another intriguing question. If dark matter shaped the cosmic web, how did those enormous filaments grow so large over time? Step far enough back in time, long before galaxies filled the sky, and the universe would look almost featureless. Not empty, but smooth. Matter existed everywhere, spread through space in an extremely uniform way. If you could somehow drift through that early universe shortly after the Big Bang, you would not see clusters of galaxies, long cosmic filaments, or enormous voids stretching across millions of light years. None of those structures existed yet. Instead, the universe resembled a hot, dense ocean of particles and radiation. Light scattered constantly between charged particles, making space glow with a bright haze. Under those conditions, gravity had not yet had time to sculpt the vast architecture we observe today. Yet hidden within that nearly uniform cosmos were tiny imperfections. These imperfections were incredibly small variations in density. Some regions contained just a little bit more matter than their surroundings, while others contained slightly less. The differences were almost unbelievably subtle. If the average density of matter in the early universe were measured, these variations would differ by only about 1 part in 100,000. That is roughly the equivalent of a single extra grain of sand within a pile containing 100,000 grains. At first glance, it might seem impossible that such tiny differences could eventually grow into the enormous structures we see today, but gravity has a particular talent for amplifying small advantages. Wherever slightly more matter existed, gravity pulled additional material inward. As more matter gathered, the gravitational pull in that region increased, attracting even more matter from its surroundings. Meanwhile, areas that began slightly less dense gradually lost material as gravity pulled it toward neighbouring regions. This process did not happen quickly. Gravity is a patient force. It does not rush. Instead, it works steadily over immense stretches of time, gently guiding matter along invisible pathways. Over millions of years, the slightly denser regions of the early universe continued collecting more material. The density contrast slowly increased. Small clumps grew larger. Large clumps merged with neighbouring clumps. What began as tiny fluctuations gradually became the first recognisable structures. Computer simulations provide a remarkable window into this process. When scientists model the early universe using the laws of physics and allow gravity to shape the distribution of matter, something fascinating happens. At first, the simulated universe looks almost perfectly smooth. Then subtle ripples begin appearing. These ripples grow, stretch, and connect with one another. Gradually, the matter organizes itself into long strands. Dense nodes appear where strands intersect, and large, empty regions open between them. After billions of simulated years, the result strongly resembles the cosmic web observed in real galaxy surveys. Filaments stretch across vast distances. Clusters sit at their intersections. Voids expand between them. The entire structure emerges naturally from gravity acting on those tiny primordial fluctuations. One useful way to picture this process is to imagine rainfall on a gently uneven landscape. At the moment the rain begins, water falls evenly across the surface. But because the land contains small slopes and depressions, the water does not remain evenly distributed. Drops begin flowing downhill towards slightly lower regions. Those small streams merge with neighbouring streams. Over time, the flow organises itself into rivers. Eventually, an entire network of waterways develops, shaped by the underlying landscape. The cosmic web formed in a somewhat similar way. The early universe contained a landscape of tiny density variations. Gravity caused matter to flow gradually towards slightly denser regions. As matter streamed inward, filaments began forming along the gravitational pathways connecting dense areas. Where several pathways converged, clusters developed. Meanwhile, regions that lost matter gradually became the vast cosmic voids observed today. Although the process sounds straightforward when described in this way, the actual evolution of cosmic structure involved an enormous amount of time. The universe is currently about 13.8 billion years old. During the first few 100,000 years, matter and radiation remained tightly coupled. Light scattered constantly, preventing matter from collapsing into dense clumps. But once the universe cooled enough for electrons and protons to combine into neutral atoms, radiation began travelling freely through space. This event, known as recombination, occurred roughly 380,000 years after the Big Bang. From that moment onward, gravity could begin shaping matter more effectively. Dark matter played an especially important role during this stage. Because dark matter does not interact with radiation the way ordinary matter does, it began forming clumps even earlier in cosmic history. These dark matter clumps created gravitational wells that attracted normal matter once the universe cooled. Gas slowly flowed into these wells, eventually forming the first stars and galaxies. The earliest galaxies were much smaller than those we see today. Over time, these young galaxies merged with neighbours, gradually building larger systems. Clusters formed as galaxies gathered in regions where multiple filaments intersected, and the cosmic web slowly became more pronounced. Interestingly, the process is still happening today. Galaxies continue moving through the cosmic web under the influence of gravity. Groups of galaxies merge into larger clusters. Clusters themselves may drift slowly toward even larger gravitational centres. The entire structure evolves over billions of years, but the pace of this evolution is incredibly slow. Even 100 million years, an almost incomprehensible span from a human perspective, represents only a small step in the life of the universe. Another curious detail about the cosmic web is that matter tends to move along filaments rather than across them. Gas and galaxies gradually flow through these structures toward denser regions. Astronomers sometimes describe filaments as cosmic highways, guiding the movement of matter across the universe. If you could watch the universe evolving over billions of years, you might see streams of galaxies drifting along these immense pathways, gradually converging at the intersections where clusters reside. Computer simulations reveal this motion clearly. In these models, matter flows along filaments like water travelling through river channels. Clusters grow larger as streams of matter feed into them. Voids expand as surrounding material migrates toward denser areas. The cosmic web becomes increasingly defined as gravity continues shaping the distribution of matter. Despite the vast scale of these structures, the physical forces involved remain surprisingly simple. Gravity is the primary driver. Tiny differences in density grow under gravitational attraction. Matter flows toward denser regions. Structures form gradually over time. What makes the cosmic web remarkable is not the complexity of the underlying physics, but the enormous scale over which these simple processes operate. Small fluctuations measured in the early universe eventually produced filaments stretching across hundreds of millions of light-years. Clusters formed containing thousands of galaxies. Voids expanded to sizes that dwarf most other cosmic structures. All of this emerged from subtle irregularities in the distribution of matter shortly after the Big Bang. Astronomers can still observe those original irregularities today. They appear in the cosmic microwave background radiation, the faint afterglow of the early universe. When scientists map this radiation, they see tiny temperature variations corresponding to the same density fluctuations that eventually produced galaxies and clusters. In other words, the blueprint of the cosmic web was already present in the universe less than 500,000 years after the Big Bang. Over billions of years, gravity transformed that blueprint into the vast structure we observe today. Another important factor influencing the growth of cosmic structure is the expansion of the universe. Space itself has been stretching ever since the Big Bang. As galaxies move farther apart due to this expansion, gravity must work against the stretching of space in order to pull matter together. During the early universe, matter density was high enough for gravity to dominate locally, allowing structures to grow. But as the universe expanded and matter became more spread out, the growth of structure slowed. In recent billions of years, another mysterious force called dark energy has begun accelerating the expansion of the universe. Dark energy pushes galaxies apart on large scales, counteracting gravity's ability to bring matter together. Because of this accelerating expansion, the cosmic web may eventually stop growing. Filaments and clusters will remain gravitationally bound structures, but the space between them will continue stretching. Over extremely long timescales, distant regions of the cosmic web may drift beyond each other's observable horizons. For now, however, the web remains an interconnected network stretching across the observable universe. Every galaxy we see, including our own Milky Way, exists somewhere within this immense structure. The Milky Way itself lies inside a filament that connects several nearby galaxy groups. Our local region belongs to a much larger structure known as the Laniakea supercluster. Within this supercluster, thousands of galaxies drift through an intricate network of gravitational pathways. Yet even these enormous structures represent only small portions of the full cosmic web. Across billions of light years, similar patterns repeat. Filaments stretch between clusters. Clusters anchor the intersections. Voids expand between them. Gravity continues guiding matter through this enormous network. Long after astronomers realized that galaxies gather into filaments and clusters, a new curiosity slowly emerged. Once scientists could map enormous portions of the universe, the next natural question became unavoidable. If the cosmic web exists everywhere, how large can its individual structures become? At first, the answer seemed straightforward. Galaxy clusters were already massive by human standards, often containing hundreds or thousands of galaxies bound together by gravity. Superclusters stretched even farther, linking clusters across distances of tens or hundreds of millions of light-years. Those numbers alone were impressive, but when astronomers began surveying larger regions of the universe, they discovered that some structures extended far beyond what anyone had expected. One of the earliest surprises arrived with the discovery of a structure called the Great Wall. The name might sound dramatic, but the structure itself truly deserved it. Identified during large galaxy surveys in the late 20th century, the Great Wall is an immense sheet of galaxies stretching across roughly 500 million light-years of space. To understand that scale, it helps to remember the size of our own galaxy. The Milky Way is about 100,000 light-years across. The Great Wall spans about 5,000 times that distance, and it is not even the largest structure scientists have found. The Great Wall was simply the first clear example that the universe contains structures of extraordinary size. These structures are not solid walls in the usual sense. They are enormous regions where galaxies are more densely distributed, forming long, thin sheets or filaments that connect clusters together. If you could somehow travel across the Great Wall, you would pass through thousands of galaxies along the way, each containing billions of stars. Yet even such immense structures are still relatively delicate. Most of the space within them remains empty. The galaxies themselves occupy only a tiny fraction of the volume. As astronomers continued mapping the universe, more discoveries followed. One of the most famous examples is the Sloan Great Wall. Discovered in data from the Sloan Digital Sky Survey, this structure extends nearly 1.4 billion light-years across. That is almost 3 times larger than the original Great Wall. The Sloan Great Wall is not a single object, but a massive collection of galaxy clusters and filaments woven together into a vast cosmic complex. Within it lie numerous clusters containing thousands of galaxies each. These clusters are connected by filaments where galaxies are arranged in long chains stretching across space. When viewed in 3-dimensional maps, the structure resembles an enormous ribbon winding through the universe. For a time, astronomers wondered whether such enormous formations might challenge the cosmological principle. The assumption that the universe should appear roughly uniform when viewed on very large scales. If structures continued growing larger and larger, perhaps the universe might turn out to be far more uneven than expected. But new discoveries continued complicating the picture. Another remarkable structure known as the Hercules Corona Borealis Great Wall was identified through studies of gamma-ray bursts. Gamma-ray bursts are extremely energetic explosions occurring in distant galaxies. Because they can be detected from across the observable universe, they provide a useful way to trace large-scale patterns. When astronomers mapped the locations of many gamma-ray bursts, they noticed a clustering of events in a region of the sky spanning billions of light-years. The resulting structure appears to extend roughly 10 billion light-years across. Now, it is important to be careful when interpreting such discoveries. Structures of this size may not represent single connected formations in the same sense as smaller cosmic filaments. Instead, they may reflect statistical groupings or alignments within extremely large regions of space. Even so, these observations suggest that the universe contains patterns stretching across truly enormous distances. Another impressive example is the Boss Great Wall, discovered using the Baryon Oscillation Spectroscopic Survey. This structure consists of multiple superclusters connected into a massive complex roughly 1 billion light-years across. The Boss Great Wall contains several large galaxy clusters linked by filaments of galaxies, forming one of the most extensive known arrangements of matter in the universe. Each time astronomers identify one of these gigantic structures, it reminds us how difficult it can be to grasp the scale of the cosmos. Our everyday experiences provide no reference points for distances measured in hundreds of millions or billions of light-years. Even light, the fastest thing in the universe, takes immense amounts of time to cross such distances. Consider a structure 1 billion light-years across. Light leaving one side of that structure would travel for 1 billion years before reaching the other side. During that time, entire civilizations could rise and fall on distant planets. Stars could form and die. Galaxies could merge with their neighbours, and still the light would be travelling. Yet despite their size, these massive formations are not isolated from the rest of the cosmic web. Instead, they are simply particularly dense regions within a much larger network. Filaments extend outward from these structures, connecting them to other clusters and superclusters. The cosmic web does not end at the boundaries of these formations. It continues outward across the observable universe. Another fascinating aspect of these giant structures is how they formed. Although gravity plays a central role, the process unfolds over extremely long periods. In the early universe, matter was distributed almost uniformly with only tiny density fluctuations. Over billions of years, gravity amplified those fluctuations. Regions that started slightly denser than average gradually attracted more matter. As matter flowed inward along gravitational pathways, filaments formed connecting clusters and superclusters. Where several filaments intersected, enormous concentrations of matter developed. These intersections eventually became the largest structures in the cosmic web. Simulations of cosmic evolution reproduce this process remarkably well. When scientists model the universe starting from the early density fluctuations measured in the cosmic microwave background, the resulting simulations produce networks of filaments strikingly similar to those observed in galaxy surveys. Clusters form at filament intersections. Filaments stretch across vast distances. Voids expand between them. And occasionally, massive walls or complexes appear where several large structures merge together. What makes these formations particularly intriguing is that they reveal the universe's structure on the largest observable scales. At smaller scales, gravity causes galaxies to gather into groups and clusters. At intermediate scales, clusters gather into superclusters. But beyond those scales, the cosmic web connects everything together. In a sense, these enormous structures represent the upper limits of cosmic architecture. They show us how matter organizes itself across billions of light-years under the influence of gravity and dark matter. Still, astronomers remain cautious about drawing final conclusions. Mapping structures on such enormous scales is challenging. The observable universe contains billions of galaxies, yet we can only measure distances for a fraction of them. Even the most advanced galaxy surveys cover only portions of the sky. As new data arrives, our understanding of cosmic structure continues evolving. Structures once thought to be the largest known may eventually be surpassed by new discoveries. Another intriguing question involves how these massive formations relate to the overall uniformity of the universe. The cosmological principle suggests that if we zoom out far enough, the universe should appear roughly the same everywhere. And indeed, when astronomers examine extremely large volumes of space, the distribution of matter does appear statistically uniform. The enormous structures we observe still fit within that larger pattern. They are like waves on the surface of an ocean. Individual waves may be large, but from far enough away the ocean itself appears smooth. The same seems to hold true for the universe. Even though the cosmic web contains vast filaments and enormous walls of galaxies, the overall structure remains consistent across the observable cosmos. Perhaps the most remarkable realization is that our own galaxy exists somewhere within this enormous network. The Milky Way sits inside a relatively modest filament connected to the Virgo cluster and other nearby galaxy groups. This region forms part of the Laniakea supercluster, which itself is just one piece of the larger cosmic web. From our perspective inside the Milky Way, the cosmic web is difficult to see directly. The vast distances involved make it impossible to observe the entire structure from within. Yet galaxy surveys and simulations allow scientists to reconstruct the network piece by piece. Every new map adds detail to the picture. Every new observation reveals additional filaments, clusters, and voids. And with each discovery, the scale of the cosmic web becomes a little clearer. Even so, these enormous structures raise an interesting question. If some of the largest formations stretch across hundreds of millions, or even billions of light years, what lies in the regions between them? Look closely at large maps of the universe, and a curious pattern begins to appear. The glowing threads of galaxies and the dense clusters where they intersect draw most of the attention, but the spaces between those structures are far more extensive. In fact, the majority of the universe's volume lies not within the filaments of the cosmic web, but inside the vast regions separating them. These regions are known as cosmic voids. The name may sound dramatic, yet it describes something surprisingly simple. A cosmic void is a region of space where galaxies are extremely scarce. Not entirely absent, but far fewer than in the surrounding filaments and clusters. When astronomers first mapped galaxies in large surveys, the void stood out almost immediately. Between the long arcs of galaxies were huge gaps in the data, areas where the dots representing galaxies simply did not appear. At first, scientists wondered if those gaps might be artifacts of observation. Perhaps telescopes had missed faint galaxies in those regions, or perhaps dust in the Milky Way was blocking the view. But as surveys expanded and instruments improved, the pattern remained consistent. The gaps were real, and they were enormous. Some cosmic voids stretch across more than 100 million light-years. Others reach even larger sizes, rivaling the scale of the largest galaxy clusters. One well-known example is the Bhuta's Void, discovered in the early 1980s. The Bhuta's Void spans roughly 250 million light-years across. To imagine such a distance is not easy. If you placed the Milky Way galaxy at one side of the void and travelled to the opposite edge at the speed of light, the journey would take 250 million years. Inside that enormous region, astronomers have found only a handful of galaxies. Compared with the crowded clusters found elsewhere in the cosmic web, the Bhuta's Void is almost empty. Still, the word empty can be misleading. Even the quietest regions of space contain something. Voids are not perfect vacuums. They contain extremely diffuse gas, faint dark matter, and occasionally small galaxies drifting in relative isolation. The density of matter inside a void is simply much lower than in the surrounding filaments. In fact, most of the universe's volume consists of these low-density regions. The cosmic web might appear dominated by filaments and clusters when we look at maps highlighting galaxies, but those structures occupy only a small fraction of the total space. Imagine blowing soap bubbles in a sink full of foam. The thin surfaces where bubbles meet form intricate patterns, but most of the volume lies inside the bubbles themselves. The cosmic web follows a similar arrangement. The filaments and walls form the thin surfaces outlining enormous bubbles of emptiness. Those bubbles are the cosmic voids. Understanding how voids form requires returning to the early universe once again. After the Big Bang, matter was distributed almost evenly throughout space, with only tiny variations in density. Some regions contained slightly more matter, while others contained slightly less. Over time, gravity amplified those differences. Denser regions gradually attracted surrounding matter, growing into filaments and clusters. Meanwhile, regions that started with slightly less matter slowly lost even more material as gravity pulled it toward nearby dense structures. As matter drained away, these regions became increasingly empty. The result was the formation of cosmic voids. This process did not involve matter suddenly disappearing. Instead, matter simply migrated outward, leaving the voids behind as the rest of the cosmic web grew denser. Computer simulations illustrate this process beautifully. In simulations of cosmic evolution, matter initially fills the simulated universe almost uniformly. But as gravity begins shaping the distribution, material flows toward denser regions along filament-like pathways. Gradually, the empty spaces between those pathways expand. Over billions of years, the voids grow larger while the surrounding filaments become more pronounced. Eventually, the simulated universe begins to resemble the cosmic web observed in galaxy surveys. Voids expand like slowly inflating bubbles between the dense strands of the web. Interestingly, voids are not completely static. They continue evolving over time. Because matter inside voids is relatively sparse, gravity within those regions is weaker than in denser parts of the universe. As a result, galaxies located inside voids tend to drift slowly outward toward the surrounding filaments. This outward motion causes voids to grow gradually larger. Meanwhile, the filaments and clusters surrounding the voids become denser as they accumulate matter from their surroundings. Another interesting detail about voids is the type of galaxies they contain. Although galaxies are rare inside voids, the few that do exist often display unusual characteristics. Many void galaxies are smaller and less crowded than galaxies found in dense clusters. Because they experience fewer gravitational interactions with neighbours, these galaxies can evolve differently. Their stars may form more slowly, and their shapes may remain relatively undisturbed for long periods. Some astronomers enjoy studying these galaxies precisely because they exist in such isolated environments. In crowded galaxy clusters, gravitational encounters are common. Galaxies can collide, merge, or have their shapes distorted by nearby neighbours. Inside voids, however, galaxies may drift for billions of years with very little disturbance. Studying these quiet systems helps scientists understand how galaxies evolve when left largely alone. Voids also play an important role in understanding the overall structure of the universe. Because voids contain relatively little matter, their expansion is influenced strongly by the overall expansion of space itself. As the universe continues expanding, voids tend to grow larger faster than denser regions. In a sense, voids act like expanding cavities within the cosmic web. Their growth helps accentuate the contrast between empty regions and dense filaments. Another reason voids are valuable to scientists is that they provide a clean environment for studying cosmology. Dense regions of space can be complicated. Galaxies interact, clusters merge, and gravitational effects from nearby structures can complicate measurements. Voids, on the other hand, are relatively simple. Their low density makes them useful laboratories for studying how the universe expands and how dark energy influences cosmic evolution. Researchers analyze the shapes and sizes of voids to test different models of cosmology. Even subtle changes in the expansion rate of the universe can affect how voids grow over time. In recent years, astronomers have also begun mapping the distribution of gas inside voids, using sensitive observations of distant quasars. Quasars are extremely bright objects powered by supermassive black holes in distant galaxies. Light from quasars travels across enormous distances before reaching Earth. Along the way, that light passes through clouds of gas scattered throughout the universe. By studying how the quasar light is absorbed by this gas, astronomers can trace the faint material filling cosmic voids. These observations reveal that even the emptiest regions of space still contain traces of matter, drifting slowly through the universe. Dark matter is also present inside voids, though at much lower densities than within filaments. Because dark matter interacts only through gravity, it tends to follow the same large-scale structure as ordinary matter. Even in regions that appear almost empty, the invisible presence of dark matter still shapes the motion of galaxies and gas. From a human perspective, the idea of a region hundreds of millions of light-years across containing almost nothing can feel difficult to imagine. Space already feels empty when we consider the distances between stars inside our own galaxy. Yet cosmic voids are emptiness on a far grander scale. If our entire Milky Way galaxy were placed inside one of the largest voids, it would likely drift through vast stretches of space without encountering another galaxy for tens or hundreds of millions of light-years. Despite this immense emptiness, voids are not merely gaps between structures. They are an essential part of the cosmic web. The web's intricate pattern exists precisely because matter has moved away from these regions over billions of years. Without voids, the filaments and clusters would not appear so clearly. Together, the filaments, clusters, and voids create the large-scale architecture of the universe. The web strands mark where matter gathered under gravity. The voids reveal where matter gradually departed, and across billions of light years, this pattern repeats again and again. Yet even with all these discoveries, astronomers continue asking an even larger question. If the cosmic web stretches across the observable universe, just how large is the full structure that we can actually see? Try to imagine standing far outside the Milky Way, somewhere deep in intergalactic space, looking back at the structure of the universe. The glowing filaments of galaxies would stretch across the darkness like an enormous network of faint lights. Clusters would appear as brighter knots where those strands meet. Between them would lie immense quiet regions where very little light appears at all. At first, this picture sounds manageable. Filaments, clusters, and voids forming a giant structure. But once astronomers began measuring the actual size of that structure, the numbers quickly became overwhelming. The cosmic web spans the entire observable universe. That phrase alone deserves a moment of explanation. The observable universe is the region of space from which light has had time to reach us since the beginning of cosmic expansion, roughly 13.8 billion years ago. Because the universe has been expanding during that time, the most distant galaxies we can currently observe are much farther away than 13.8 billion light-years. In fact, the observable universe stretches about 93 billion light-years across. That means if you could travel in a straight line from one edge of the observable universe to the opposite side, the distance would be roughly 93 billion light-years. Inside that enormous volume lies the cosmic web. Every galaxy we can see belongs somewhere within this vast structure. Each filament connects clusters across enormous distances, and the network continues in every direction for billions of light-years. Even the largest structures we discussed earlier, the Great Walls and massive supercluster complexes, are only pieces within this much larger framework. To understand how the cosmic web fills such an enormous region, it helps to consider the scale of individual components. Typical galaxy clusters measure several million light-years across. They contain hundreds or thousands of galaxies bound together by gravity. Superclusters extend much farther, sometimes reaching hundreds of millions of light-years in length. These structures link multiple galaxy clusters along extended filaments. Filaments themselves can stretch across hundreds of millions of light-years. But the web does not stop there. Those filaments continue connecting superclusters across distances approaching 1 billion light-years or more, and all of these structures together form the vast network spanning the observable universe. Another way to picture this scale is to imagine a three-dimensional map of galaxies covering the entire visible cosmos. When astronomers plot millions of galaxies in space, the result resembles a giant lattice or foam-like structure. The filaments trace long arcs through space. Clusters glow at the intersections. Voids form huge empty bubbles between the strands, and the entire network fills the enormous sphere of the observable universe. Yet despite its size, the cosmic web is surprisingly delicate. Most of the universe is still empty space. Even within filaments, galaxies remain separated by millions of light-years. The visible matter that outlines the web occupies only a tiny fraction of the total cosmic volume. If you could shrink the entire observable universe down to the size of a globe, the galaxies would resemble faint dust particles scattered along thin threads wrapping around the surface. The threads themselves would outline huge cavities representing cosmic voids. This structure raises another interesting question. Does the cosmic web end somewhere? The honest answer is that we do not know. Our observations are limited by the speed of light and the age of the universe. Light from extremely distant regions simply has not had enough time to reach Earth yet. Beyond the observable universe, the cosmic web may continue indefinitely. In many cosmological models, the universe extends far beyond the region we can see. If that is true, the cosmic web may stretch across a far larger cosmic landscape, repeating its pattern of filaments and voids across unimaginable distances. Some scientists suspect that the universe could be vastly larger than the observable portion, perhaps even infinite. If the universe is indeed infinite, the cosmic web might extend endlessly in all directions, forming an infinite network of galaxies spread throughout space. However, because we cannot observe beyond the cosmic horizon, this remains an open question. All we can measure directly is the structure within the observable universe. Within that region, the cosmic web appears remarkably consistent. Galaxy surveys covering different portions of the sky reveal similar patterns of filaments, clusters, and voids. The Sloan Digital Sky Survey, the Dark Energy Survey, and several other large mapping projects have traced millions of galaxies across billions of light years. Each survey confirms the same general architecture. The web continues across every region scientists have examined. The scale of these surveys has grown dramatically over the past few decades. Early galaxy maps contained only thousands of galaxies. Modern surveys include millions. Future projects may map tens or even hundreds of millions of galaxies across the sky. As these maps expand, they allow astronomers to trace filaments across larger and larger distances. The more data scientists gather, the clearer the cosmic web becomes. Interestingly, the cosmic web also reveals something important about the universe's overall uniformity. At smaller scales, the universe looks highly structured. Galaxies cluster into groups, clusters gather into superclusters, and filaments connect those superclusters across vast distances. But if astronomers examine extremely large volumes of space, hundreds of millions or billions of light years across, the universe begins to appear statistically uniform. This idea is known as the scale of homogeneity. Beyond a certain scale, the distribution of matter becomes roughly even when averaged across enormous regions. In other words, although the cosmic web contains large structures, those structures do not grow indefinitely larger. At some scale, the universe looks smooth again. Current observations suggest that this transition occurs at scales of roughly 300 million light-years or so. Below that scale, the cosmic web dominates. Above it, the universe appears more uniform when averaged across huge volumes. This balance between structure and uniformity helps support the cosmological principle, the idea that the universe has no preferred location or direction when viewed on the larger scales. Every region of the universe appears statistically similar when examined across vast distances. From that perspective, the cosmic web represents the largest visible pattern produced by gravity and dark matter within the observable cosmos. Another fascinating aspect of the cosmic web's size involves how light travels through it. Because the web spans such enormous distances, light from distant galaxies must cross multiple filaments, clusters, and voids before reaching Earth. During that journey, the light may be bent slightly by gravity, absorbed by intergalactic gas, or stretched by the expansion of space itself. Astronomers study these effects carefully to learn more about the distribution of matter across the web. Gravitational lensing, for example, allows scientists to detect dark matter along filaments by observing how it bends light from distant galaxies. Quasar light passing through intergalactic gas reveals the faint material filling the cosmic web's strands. Each observation adds another piece to the map of this enormous structure. Still, even with all these tools, astronomers are only beginning to explore the cosmic web in detail. Large portions of the universe remain unmapped. Future telescopes and surveys will continue expanding our view, revealing more of the network connecting galaxies across billions of light years. And somewhere within that vast structure lies our own cosmic neighbourhood. Because the Milky Way does not float randomly through space, our galaxy occupies a specific location within the cosmic web. It sits inside a filament connected to nearby galaxy groups and clusters. Understanding that location helps astronomers trace how matter flows through the web and how galaxies migrate along its strands over time. Looking at the cosmic web from this perspective can feel both humbling and strangely comforting. Our galaxy is just one tiny point within a network stretching across tens of billions of light years. Yet that same network connects us to countless other galaxies scattered throughout the universe. The cosmic web forms the grand structure in which every galaxy, every star, and every planet exists. And somewhere along one of its quiet filaments lies the place we call home. But identifying where our galaxy fits within that enormous network leads naturally to another question. Where exactly are we located within the cosmic web itself? Picture the Milky Way not as the centre of anything special, but as one small resident inside a much larger cosmic neighbourhood. Astronomers used to wonder whether our galaxy might occupy a privileged position in the universe. After all, from Earth, the night sky surrounds us evenly in every direction. It can give the impression that we sit at the middle of the cosmic stage, yet careful measurements gradually replace that old intuition with a far more modest truth. Our galaxy is simply one node along one strand of the cosmic web. To understand that position, it helps to zoom outward step by step, beginning with the scale closest to home. The Milky Way is a large spiral galaxy, roughly 100,000 light-years across. It contains hundreds of billions of stars, vast clouds of gas and dust, and a supermassive black hole at its centre. Around it orbit smaller satellite galaxies, including the large and small Magellanic Clouds. For a long time, astronomers thought the Milky Way might represent a fairly typical isolated system drifting through space. But once telescopes began discovering other galaxies in large numbers, it became clear that galaxies rarely travel alone. Instead, they often gather into small gravitational families. The Milky Way belongs to one of these families called the Local Group. The Local Group contains more than 50 known galaxies, although most of them are quite small. The largest members are the Milky Way itself, the Andromeda Galaxy, and a somewhat smaller spiral known as the Triangulum Galaxy. Andromeda lies about 2.5 million light-years away from us, making it the closest large galaxy to the Milky Way. It is slightly larger than our own galaxy, and contains perhaps 1 trillion stars. Although that distance sounds enormous, by cosmic standards it is quite small. The galaxies in the Local Group remain gravitationally bound together. Over billions of years they drift slowly through space, influenced by one another's gravity. In fact, the Milky Way and Andromeda are gradually moving toward each other. Astronomers expect the two galaxies to collide and merge several billion years from now. Despite the drama such a merger might sound like, the vast distances between stars mean that actual stellar collisions would be extremely rare. Still, that future encounter reminds us that our galaxy's motion is guided by the larger structure around it. Beyond the Local Group lies a far larger gathering of galaxies. Our galaxy family sits within a region known as the Virgo supercluster. The Virgo supercluster stretches across more than 100 million light-years and contains thousands of galaxies organised into clusters and smaller groups. Near the centre of this supercluster lies the Virgo cluster, a massive collection of more than 1,000 galaxies located roughly 55 million light-years away. The Virgo cluster acts as one of the gravitational anchors of our local cosmic region. Many galaxies in the surrounding area drift slowly toward it along the filaments of the cosmic web. Yet even the Virgo supercluster is not the full story. During the past decade, astronomers have refined their understanding of the structure surrounding our galaxy and discovered something even larger. The Virgo supercluster turns out to be part of an enormous region known as the Laniakea supercluster. The name Laniakea comes from Hawaiian words meaning immeasurable heaven, a fitting description for such an immense structure. Laniakea spans roughly 520 million light-years across and contains around 100,000 galaxies. Instead of being a tightly bound cluster, Laniakea is more like a vast basin in the cosmic landscape. Galaxies within this region tend to drift along gravitational pathways toward a central area known as the Great Attractor. The Great Attractor is a region of unusually strong gravitational influence, located about 250 million light-years away from the Milky Way. Although much of this region lies hidden behind dust from our own galaxy, observations suggest that enormous concentrations of galaxies reside there. The motion of galaxies within Laniakea appears to flow gradually toward this gravitational centre. Astronomers discovered this pattern by measuring the peculiar velocities of galaxies. Normally, galaxies move away from each other because the universe itself is expanding. But on smaller scales, gravity can alter those motions slightly. By measuring how galaxies move relative to the general cosmic expansion, scientists can determine the gravitational flows shaping their motion. When researchers analyse these flows across a large region of space, they notice something remarkable. Galaxies seem to follow large-scale streams, gradually drifting along filaments toward dense regions. The boundaries of these flows define the edges of the Laniakea supercluster. In a sense, the galaxies of Laniakea behave like raindrops flowing across a landscape toward a shared basin. Our Milky Way sits quietly within one of those streams. From this perspective, our galaxy is not stationary. It is slowly moving through the cosmic web along a filament connecting nearby galaxy groups. The speeds involved are enormous by everyday standards. The Milky Way travels through space at hundreds of kilometers per second relative to the cosmic microwave background. Yet the distances between galaxies are so vast that even these speeds result in very gradual changes over cosmic time. If we zoom out even farther, Laniakea itself becomes just one component of a much larger network. Superclusters connect to one another through extended filaments that span hundreds of millions of light-years. These filaments weave together across the observable universe, forming the cosmic web. Our galaxy therefore sits several layers deep within this structure. First comes the solar system orbiting inside the Milky Way. Next comes the Milky Way as part of the local group. The local group resides within the Virgo supercluster. The Virgo supercluster belongs to the larger Laniakea region, and Laniakea itself forms just one node within the immense cosmic web stretching across billions of light-years. Looking at the universe in this layered way can be both humbling and fascinating. At each step outward, the scale expands dramatically. Planets orbit stars. Stars gather into galaxies. Galaxies cluster into groups. Groups connect into superclusters. Superclusters link together across enormous filaments spanning the cosmos. Our everyday experience takes place on the smallest of those scales. Yet our planet ultimately exists within this much larger network. Another interesting detail about our position in the cosmic web involves the direction of galactic flows. Galaxies in our region appear to move gradually toward the Virgo cluster and beyond toward the Great Attractor. These motions are influenced by the gravitational pull of massive structures distributed throughout the web. At the same time, cosmic expansion pushes galaxies farther apart on larger scales. The result is a subtle balance between gravity pulling matter together and expansion stretching space outward. Our galaxy's journey through the web reflects that balance. Over billions of years, galaxies migrate slowly along filaments. Clusters grow where those filaments intersect. Voids expand as surrounding matter flows away. The cosmic web evolves gradually under the combined influence of gravity and cosmic expansion. Even though our galaxy occupies only a tiny point within this structure, studying our position helps astronomers understand how the entire web behaves. By mapping the motions of nearby galaxies, scientists can trace the invisible gravitational landscape guiding their movement. These maps reveal how matter flows along filaments and accumulates within clusters, and they provide clues about the distribution of dark matter shaping the web's structure. Perhaps the most remarkable realization is that every galaxy shares a similar story. Each one occupies its own place within the cosmic web. Some lie within dense clusters surrounded by thousands of neighbours. Others drift quietly along remote filaments. A few reside deep inside cosmic voids, isolated from most other galaxies. Yet all of them remain connected through the same vast network stretching across the observable universe. Our galaxy may feel enormous when viewed from the perspective of Earth. but within the cosmic web it becomes just one small participant in a structure spanning tens of billions of light years. And while that scale can feel overwhelming, it also reveals something quietly beautiful. Every star we see in the night sky ultimately belongs to a galaxy woven into the same cosmic web as countless others. From that point of view, the universe is not just a collection of isolated islands. It is a connected system, stretching across unimaginable distances. Light leaving a distant galaxy begins a journey so long that it often starts before Earth even existed. Photons stream outward from stars, nebulae, and glowing gas clouds, carrying information about their origins across billions of years. Eventually, some of that light reaches telescopes on our planet, allowing astronomers to reconstruct the structure of the universe. Yet the path those photons follow is rarely simple. Between the distant galaxy and Earth lies the vast architecture of the cosmic web, and every filament, cluster, and void along the way subtly influences the journey. To appreciate this process, it helps to remember just how far light must travel to reach us. The nearest large galaxy, Andromeda, lies about 2.5 million light-years away. That means the light-entering telescopes tonight left Andromeda when early human ancestors were just beginning to shape stone tools. But Andromeda is practically next door compared with the distant galaxies astronomers routinely observe. Many galaxies studied in modern surveys lie billions of light-years away. Their light began travelling toward us when the universe itself was far younger. During that long trip, photons passed through enormous regions of space filled with structures that were unknown to astronomers until relatively recently. The cosmic web forms the environment through which nearly all extragalactic light must move. Filaments containing galaxies, vast clouds of intergalactic gas, clusters packed with dark matter, and the quiet expanses of cosmic voids all lie along the route. Although light travels incredibly fast, the conditions it encounters can change its path in subtle ways. One of the most important influences comes from gravity. According to Einstein's theory of general relativity, massive objects bend the fabric of space and time around them. When light travels through those curved regions, its path bends slightly as well. This effect is known as gravitational lensing. Galaxy clusters are particularly strong gravitational lenses. They contain enormous amounts of mass, including large halos of dark matter surrounding the galaxies themselves. When light from more distant galaxies passes near such a cluster, the gravity of the cluster can bend the light's trajectory. From Earth, this bending can produce remarkable visual effects. Sometimes the background galaxy appears stretched into long arcs of light surrounding the cluster. In other cases, the light splits into multiple images, creating mirror-like copies of the same distant object. Astronomers use these lensing effects to learn about both the foreground clusters and the background galaxies whose light is being distorted. The strength of the lensing reveals how much mass the cluster contains, including the dark matter that cannot be seen directly. Gravitational lensing also allows astronomers to detect the faint filaments of the cosmic web itself. Even when those filaments contain little visible matter, their dark matter can still bend, passing light slightly. By measuring extremely subtle distortions in the shapes of distant galaxies, scientists can reconstruct maps of the invisible mass between them. In this way, the cosmic web quietly reveals itself through the journey of light. Gravity is not the only influence photons encounter during their trip through intergalactic space. Along many filaments of the cosmic web lies a thin but widespread component known as the intergalactic medium. This medium consists mostly of hydrogen gas spread across enormous volumes of space. The density is extraordinarily low, sometimes only a few atoms per cubic meter, yet the gas stretches along the same filaments that connect galaxy clusters. When light from a distant quasar or galaxy passes through these clouds of gas, specific wavelengths of the light are absorbed by hydrogen atoms. Each cloud leaves a tiny fingerprint in the spectrum of the light. Astronomers study these absorption patterns in great detail. The result is something called the Lyman alpha forest. a sequence of absorption lines that appear in the spectra of distant quasars. Each line corresponds to a cloud of hydrogen gas located somewhere between the quasar and Earth. By analysing the pattern of these lines, scientists can map the distribution of gas along the line of sight. What they find is striking. The gas traces the same filamentary structure seen in galaxy surveys. Even in regions where galaxies are sparse, the faint intergalactic medium outlines the underlying cosmic web. In effect, light from distant quasars acts like a probe passing through the universe, revealing the structure of matter along its path. The expansion of the universe also shapes the journey of light across the cosmic web. As space expands, the wavelength of travelling light stretches. This stretching shifts the light toward the red end of the spectrum, a phenomenon known as cosmological redshift. The farther light travels, the more space expands during its journey, and the greater the redshift becomes. Astronomers use this effect to estimate the distances of distant galaxies and quasars. But redshift also tells us something about how long light has been travelling through the cosmic web. Photons arriving from extremely distant objects may have spent billions of years crossing filaments, voids, and clusters before finally reaching our telescopes. Along that route, the universe itself continues evolving. Galaxies move, clusters grow, and the cosmic web slowly reshapes itself under gravity. In a sense, every beam of light we observe carries a record of the universe's history along its path. There is another subtle effect that occurs when light passes through massive regions of the cosmic web. This phenomenon is known as the integrated Sachs-Wolf effect. As photons travel through gravitational wells formed by clusters and filaments, they gain energy while falling inward and lose energy while climbing back out. In a static universe, those changes would cancel out perfectly. However, because the universe is expanding and dark energy is accelerating that expansion, the gravitational landscape changes slightly during the photon's journey. This can leave a small imprint on the energy of the light, particularly in the cosmic microwave background radiation. By studying these faint signals, astronomers gain additional information about the distribution of matter and the influence of dark energy across the cosmic web. The journey of light through the universe therefore acts like a grand observational tool. Each photon carries clues about the structures it encountered along the way. Modern telescopes and instruments have become remarkably skilled at decoding those clues. Observatories both on Earth and in space measure the brightness, colour, and spectra of distant objects with extraordinary precision. Large surveys gather data from millions of galaxies, allowing scientists to reconstruct three-dimensional maps of the cosmic web. Space-based telescopes such as the Hubble Space Telescope and the James Webb Space Telescope contribute detailed observations of distant galaxies whose light has travelled across much of the observable universe. Meanwhile, radio observatories and upcoming instruments like the Square Kilometre Array aim to detect the faint hydrogen gas tracing the web's filaments. All of these observations depend on light making its long journey through the cosmic web to reach us. It is worth remembering that when astronomers observe extremely distant galaxies, they are not seeing those galaxies as they exist today. They are seeing them as they were when their light first began travelling toward Earth. A galaxy observed at a distance of 10 billion light-years appears to us as it existed 10 billion years ago. In this way, light does more than reveal the structure of the cosmic web. It also allows us to see how that structure evolved over time. By observing galaxies at different distances, astronomers effectively look back through different stages of cosmic history. Closer galaxies show the web as it appears in the relatively recent universe. More distant galaxies reveal earlier stages when the web's filaments were still forming and clusters were smaller. These observations allow scientists to piece together the story of how the cosmic web grew from tiny density fluctuations after the Big Bang into the enormous network we observe today. And the process continues. Every moment, new light from distant galaxies begins its long journey across the cosmic web. Some of it will travel for billions of years before reaching observers on Earth, or perhaps civilizations on other planets somewhere in the universe. Along the way, it will pass through the same vast network of filaments, clusters, and voids that connect galaxies across the cosmos. When that light finally arrives, it will bring with it a message from a distant corner of the universe, carrying traces of everything it encountered along the way. Those traces help astronomers understand not only where galaxies are located, but how matter flows through the cosmic web itself. Galaxies rarely stay exactly where they first formed. Over immense stretches of time, they drift through space under the influence of gravity, following pathways shaped by the larger structure of the universe. Those pathways are not random. They're guided by the filaments and clusters that make up the cosmic web, and the movement of galaxies along those strands reveals something important about how matter behaves on the larger scales. To understand that movement, imagine once again the web-like structure astronomers have mapped across the universe. Filaments stretch across hundreds of millions of light-years. At their intersections lie galaxy clusters containing enormous concentrations of matter. Between those structures sit the vast voids where galaxies are rare. Gravity pulls matter toward the densest regions of this network. Over billions of years, galaxies gradually migrate along the filaments toward the nodes where clusters reside. This process is extremely slow compared with human timescales, but across cosmic history it becomes quite significant. One way scientists describe this motion is by thinking of the cosmic web as a network of gravitational currents. Just as water flows downhill through river channels, matter in the universe flows along the filaments of the web toward regions of stronger gravitational attraction. Gas, dark matter, and entire galaxies all participate in this slow movement. Computer simulations illustrate this behavior clearly. When researchers model the evolution of the universe using dark matter and gravity, they observe streams of matter forming along filaments. These streams carry material inward toward clusters where multiple filaments intersect. Galaxies forming within those streams tend to follow the same paths. They move gradually along the filaments, sometimes merging with other galaxies along the way. Eventually, many of them arrive at the dense environments of galaxy clusters. Once inside a cluster, the gravitational interactions become much more complex. Clusters contain hundreds or thousands of galaxies moving at high speeds relative to one another. Collisions between galaxies remain rare because the distances between stars are enormous, but gravitational encounters can still reshape galaxies over time. Some galaxies may merge with larger neighbours, forming new systems with combined masses and altered shapes. Others may lose gas through interactions with the hot plasma filling the cluster, gradually slowing the formation of new stars. In this way, clusters act as cosmic gathering points, where galaxies accumulate and evolve under strong gravitational influence. The movement of galaxies along filaments can also help explain why clusters continue growing even today. Clusters do not simply appear fully formed in the early universe. Instead, they grow gradually by attracting surrounding matter. Filaments act like supply routes delivering fresh material. Gas flows inward along these structures, fueling star formation in galaxies along the way. Dark matter also flows along the same gravitational channels, strengthening the mass of the cluster as it accumulates. Occasionally, entire groups of galaxies travel together along a filament before eventually merging with a larger cluster. Astronomers sometimes observe such events in progress. In some cases, a smaller cluster can be seen falling into a larger one, producing enormous shock waves in the hot gas filling the cluster environment. These collisions release tremendous amounts of energy and can reshape the structure of the clusters involved. Despite the dramatic nature of these encounters, the overall flow of matter through the cosmic web remains surprisingly orderly. Large-scale simulations reveal that galaxies tend to follow the same general directions over long periods. The gravitational pull of massive structures guides their movement along the web's filaments. In many ways, the motion resembles traffic moving through a network of highways. Cars do not wander randomly across the landscape. They follow roads that connect cities. Similarly, galaxies move along filaments that connect clusters. These filaments provide the gravitational pathways guiding matter across enormous distances. Interestingly, the directions of galaxy spins sometimes reflect this flow. Studies have found that the orientation of galaxies can correlate with the filaments in which they reside. Spiral galaxies often rotate in directions related to the structure of their surrounding filament. This suggests that the formation and growth of galaxies may be influenced by the large-scale flows of matter feeding them. As gas flows along a filament into a forming galaxy, it can help determine how the galaxy spins and evolves. Another intriguing aspect of these flows involves the motion of entire galaxy groups. The local group itself is not stationary. Our galaxy cluster drifts slowly through space under the gravitational influence of nearby structures. Astronomers have measured the motion of the Milky Way relative to the cosmic microwave background, the faint radiation left over from the early universe. Those measurements reveal that our galaxy moves at roughly 600 kilometers per second in a particular direction through space. Part of this motion results from the gravitational pull of massive regions such as the Virgo cluster and the mysterious area known as the Great Attractor. These massive structures lie along the larger filaments of the cosmic web. The gravitational influence they exert helps shape the motion of galaxies across hundreds of millions of light years. From this perspective, the cosmic web is not merely a static pattern of galaxies. It is a dynamic system where matter continually shifts under the influence of gravity. Galaxies flow along filaments. Clusters grow as they attract surrounding matter. Voids expand as material drains away from them. Over billions of years, the structure of the web gradually becomes more pronounced. The density contrast between filaments and voids increases. Clusters accumulate more galaxies, and the entire network evolves as cosmic expansion and gravity compete with one another. Cosmic expansion pushes galaxies apart on very large scales, while gravity pulls matter together within filaments and clusters. The balance between these forces shapes how galaxies move through the web. In regions where gravity dominates, galaxies gather into clusters and superclusters. In regions where expansion dominates, voids grow larger and emptier. The flows of galaxies along filaments therefore represent the universe gradually organizing itself. Another important element in this process involves the intergalactic gas flowing through the web. Gas streaming along filaments can feed galaxies with fresh material needed for star formation. This process, sometimes called cold accretion, allows galaxies to continue forming stars over long periods. Without such inflows of gas, galaxies might exhaust their supply of star-forming material much more quickly. Filaments therefore serve not only as pathways for galaxies, but also as channels supplying gas and dark matter to growing systems. In some observations, astronomers have detected enormous streams of gas connecting galaxies across hundreds of thousands of light years. These structures appear to trace the same filaments predicted by simulations of the cosmic web. Although the gas is extremely faint, modern instruments are beginning to reveal its presence more clearly. Each new observation helps scientists understand how matter circulates through the cosmic network. Looking far into the future, the flows of galaxies along the cosmic web will eventually change. As dark energy accelerates the expansion of the universe, distant structures will gradually move beyond one another's gravitational influence. Filaments that currently connect clusters may stretch and thin as space expands. Clusters themselves will remain gravitationally bound, but the distances between them will grow ever larger. For now, however, the cosmic web remains a vibrant system of interconnected structures guiding the motion of galaxies across billions of light years. The Milky Way participates in this motion just like any other galaxy. Slowly, almost imperceptibly from our perspective, our galaxy drifts along its filament within the larger Laniakea region. Over billions of years, those movements contribute to the ongoing evolution of the web. Gas flows, galaxies migrate, clusters grow, and voids expand. And through it all, the cosmic web continues shaping the universe on the larger scales. Between the bright galaxies that outline the cosmic web lies something far quieter and far harder to see. When people imagine intergalactic space, they often picture an enormous vacuum, a vast emptiness where almost nothing exists. Compared with the crowded environments inside galaxies, that description is not entirely wrong. Yet space between galaxies is not completely empty. Instead, it contains an extremely thin mist of gas spread across unimaginable distances. This material is known as the intergalactic medium. Although it is faint and difficult to observe directly, the intergalactic medium plays a major role in the structure and evolution of the cosmic web. In fact, most of the ordinary matter in the universe is believed to reside in this diffuse gas rather than inside stars or galaxies. To understand how surprising that is, consider the matter we are most familiar with. Stars, planets, nebulae, and the glowing disks of galaxies dominate astronomical images. They appear bright and dramatic, filling photographs of the universe with colour and detail. But those luminous objects represent only a small portion of the universe's normal matter. The majority of ordinary atoms exist outside galaxies in vast reservoirs of gas stretched along the filaments of the cosmic web. This gas is incredibly thin. In some regions, the density may be only a few hydrogen atoms per cubic meter. For comparison, the air you breathe contains roughly 10 trillion molecules in the same volume. From a human perspective, such a low density seems almost indistinguishable from emptiness. Yet because the intergalactic medium occupies such enormous volumes of space, its total mass becomes significant. The gas fills the filaments connecting galaxy clusters, outlining the same web-like structure traced by galaxies themselves. Astronomers did not immediately realize how much matter existed in this diffuse form. For many years, observations suggested that a large fraction of the universe's ordinary matter appeared to be missing. Calculations based on the early universe indicated how much normal matter should exist today. But when astronomers added up all the matter visible in stars and galaxies, they found only about half of the expected amount. This puzzle became known as the missing baryon problem. Baryons are particles such as protons and neutrons that make up ordinary matter. If stars and galaxies accounted for only part of the total baryons in the universe, the rest had to be hiding somewhere else. Eventually, astronomers began suspecting that the missing matter might exist in the intergalactic medium. Detecting such faint gas directly is difficult because it emits very little light. However, astronomers found a clever method to reveal its presence. They used distant quasars as cosmic flashlights. Quasars are extremely bright objects powered by supermassive black holes at the centres of distant galaxies. Their intense radiation shines across billions of light years, travelling through the cosmic web before reaching Earth. As quasar light passes through clouds of intergalactic gas, specific wavelengths of the light are absorbed by hydrogen atoms. These absorption features appear as dark lines in the spectrum of the quasar's light. Each cloud of gas along the line of sight leaves its own fingerprint. When astronomers examine the spectra of distant quasars, they often find dozens or even hundreds of these absorption lines. Together they form what scientists call the Lyman alpha forest. Each line in this forest represents a cloud of hydrogen gas somewhere between the quasar and Earth. By studying these lines carefully, astronomers can determine the location, density, and motion of the gas clouds that produced them. What emerges from these observations is a remarkable picture. The gas does not appear randomly distributed. Instead, it traces the same filamentary patterns revealed by galaxy surveys. The intergalactic medium flows along the filaments of the cosmic web, connecting clusters and surrounding galaxies. In some ways, the gas outlines the web even more clearly than the galaxies themselves. Galaxies form in the densest regions of these filaments, but the gas extends farther, filling much of the space along the strands. Beyond the cool hydrogen clouds detected through the Lyman alpha forest, astronomers have also identified another component of the intergalactic medium, known as the warm-hot intergalactic medium. This gas is heated to temperatures of hundreds of thousands or even millions of degrees. At such high temperatures, the gas becomes highly ionized and emits faint X-rays rather than visible light. Detecting this hot gas requires extremely sensitive space-based telescopes capable of observing X-ray radiation. Observations from instruments such as the Chandra X-ray Observatory and XMM Newton have revealed traces of this hot material within cosmic filaments. These discoveries suggest that a large portion of the universe's missing baryons may reside in these warm hot gas streams. The heating of this gas occurs partly because of shock waves generated as matter flows through the cosmic web. As gas falls toward clusters along filaments, gravitational energy converts into heat. Large-scale collisions between galaxy clusters can also produce enormous shock fronts travelling through the intergalactic medium. These shock waves heat the gas and redistribute it across the web. Another important role of the intergalactic medium involves feeding galaxies. Galaxies require gas to form new stars. Inside galaxies, star formation gradually consumes available gas, converting it into stellar material over millions of years. Without a fresh supply of gas, galaxies would eventually run out of fuel for star formation. The cosmic web provides that supply. Gas flows along filaments toward galaxies embedded within them. As the gas approaches a galaxy, gravity pulls it inward, allowing it to join the galaxy's disk or halo. This process is sometimes called cold accretion. Unlike the hot gas found in galaxy clusters, cold accretion streams can deliver relatively cool gas directly into galaxies, providing fresh material for new stars to form. Simulations of galaxy formation show these gas streams clearly. In the simulations, narrow rivers of gas flow along filaments toward galaxies, feeding their growth over billions of years. Without these inflows, galaxies might exhaust their gas much earlier in cosmic history. Observations are beginning to confirm the presence of such streams. Astronomers have detected faint hydrogen emissions and absorption signatures consistent with gas flowing into galaxies from the surrounding cosmic web. Although these structures are difficult to observe directly, their effects are becoming increasingly clear. The intergalactic medium also carries chemical elements produced by stars. When massive stars explode as supernovae, they release heavy elements into the surrounding space. Some of this material escapes from galaxies and spreads into the intergalactic medium. Over time, the cosmic web becomes enriched with elements such as carbon, oxygen, and silicon produced by earlier generations of stars. Studying these elements helps astronomers understand how galaxies interact with their environments and how matter circulates through the universe. The presence of heavy elements in the intergalactic medium reveals that galaxies do not evolve in isolation. They exchange matter with the surrounding cosmic web. Gas flows into galaxies to form stars. Supernova explosions and galactic winds push enriched material back into the intergalactic medium. This ongoing exchange forms part of a much larger cosmic cycle. Despite its importance, the intergalactic medium remains one of the most challenging components of the universe to observe. Its extremely low density means it emits very little light. Most of what astronomers know about it comes from indirect observations such as absorption lines and faint emissions detected with highly sensitive instruments. Future telescopes may reveal even more detail. New observatories designed to detect faint ultraviolet and X-ray signals could map the gas within cosmic filaments more clearly than ever before. These observations may eventually allow astronomers to create detailed maps of the intergalactic medium throughout the cosmic web. Such maps would show not only where galaxies are located, but also how gas flows through the network connecting them. Understanding that flow is essential for explaining how galaxies grow and evolve over cosmic time. The cosmic web, after all, is not just a static arrangement of galaxies. It is a dynamic system where gas, dark matter, and galaxies move slowly through an enormous gravitational landscape. Within that landscape, the faint gas between galaxies forms a crucial component of the universe's structure. Long before astronomers could observe the cosmic web in detail, scientists were already trying to understand how such a structure might form. The challenge was enormous. The universe contains billions of galaxies spread across billions of light years, all interacting through gravity, dark matter, gas dynamics, and cosmic expansion. Trying to predict how all of that evolves over time is far beyond what a person could calculate by hand. So researchers turned to a powerful tool, supercomputers. A supercomputer allows scientists to simulate the universe by modelling the laws of physics that govern matter and energy. Instead of observing cosmic history passively through telescopes, researchers can recreate the universe inside a computer program and watch how structure forms over billions of years. The idea sounds almost like science fiction, but the principle is surprisingly straightforward. Scientists begin by describing the early universe shortly after the Big Bang. Observations of the cosmic microwave background provide an extremely detailed map of the tiny density fluctuations that existed at that time. These fluctuations represent the initial conditions from which galaxies and cosmic structures eventually formed. Inside a simulation, the universe begins as a vast grid filled with particles representing matter. Each particle stands for a large amount of mass, often containing millions or even billions of times the mass of the Sun. The computer then applies the laws of gravity to these particles. Every particle pulls on every other particle. As time moves forward in the simulation, the particles begin drifting towards slightly denser regions, just as matter did in the real universe. Gradually, the distribution of matter becomes uneven. Dense clumps appear. Filaments begin stretching between those clumps. Voids expand where matter flows away. Over billions of simulated years, the cosmic web begins to emerge. When scientists first ran these simulations decades ago, the results were astonishing. Without anyone telling the computer to form filaments or clusters, the simulated universe naturally produced the same web-like patterns that astronomers were beginning to detect in galaxy surveys. Gravity alone, acting over enormous spans of time, was enough to produce the cosmic web. One of the earliest influential simulations was known as the Millennium Simulation. This project, completed in the early 2000s, used billions of particles to model the growth of cosmic structure within a region of space roughly 2 billion light-years across. The simulation tracked the evolution of dark matter under gravity for billions of years, beginning shortly after the Big Bang. As the simulation progressed, dark matter particles gradually formed a vast network of filaments and clusters. When the results were visualized, the pattern looked remarkably similar to maps of the real universe. Bright nodes marked the locations where clusters formed. Thin strands connected them across enormous distances. Large, empty regions appeared between the filaments. The resemblance between simulation and observation was striking. It confirmed that the cosmic web could arise naturally from the physics of gravity and the initial conditions present in the early universe. Since then, simulations have grown even more sophisticated. Modern supercomputers can track tens of billions of particles simultaneously. These simulations include not only dark matter but also the behavior of gas, star formation, supernova explosions, and the growth of supermassive black holes. Programs such as Illustra's, Eagle, and TNG-50 attempt to recreate entire cosmic volumes with increasing detail. Instead of representing only dark matter, they model how galaxies form inside the web. Gas flows along filaments toward dense regions. Stars ignite within collapsing clouds. Black holes release enormous energy that can influence surrounding galaxies. All of these processes interact within the evolving cosmic web. The results help scientists understand why galaxies appear the way they do today. One fascinating discovery from these simulations is how strongly galaxies depend on their location within the cosmic web. Galaxies embedded in dense filaments tend to grow more rapidly because they receive a steady supply of gas flowing along those structures. Clusters at filament intersections become crowded environments where galaxies interact frequently. Meanwhile, galaxies that form inside cosmic voids experience far fewer interactions and may evolve more slowly. In this way, the cosmic web acts as a framework guiding the growth of galaxies across the universe. Simulations also reveal something important about dark matter. Although dark matter cannot be seen directly, its gravitational influence shapes the entire cosmic web. In most simulations, dark matter forms the underlying skeleton of the universe. Ordinary matter, the atoms that form stars and galaxies, falls into the gravitational wells created by dark matter. As gas collects within these wells, galaxies eventually form along the same filaments traced by the invisible dark matter network. Without dark matter, the simulations fail to reproduce the large-scale structures observed in the real universe. The cosmic web would look very different, and galaxies might not form as efficiently as they do. Another benefit of supercomputer simulations is that scientists can experiment with different cosmological conditions. Researchers can adjust parameters such as the amount of dark matter, the strength of dark energy, or the density fluctuations present in the early universe. By comparing the results with real observations, scientists can test which models best match reality. If a particular simulation produces a cosmic web that closely resembles the one observed through telescopes, it provides strong evidence that the underlying physics in the model is correct. In this way, simulations become powerful laboratories for studying the universe. They allow astronomers to explore scenarios that would be impossible to test directly. For example, scientists can run simulations covering the entire age of the universe, compressing billions of years of cosmic evolution into a sequence that can be viewed in minutes or hours. Watching such simulations unfold can be strangely mesmerizing. At first, the universe appears nearly uniform. Then tiny fluctuations begin to grow. Filaments stretch outward. Clusters gather at intersections. Voids expand between them. Eventually, the cosmic web takes shape, forming a network that strongly resembles the one astronomers observe today. These visualizations provide a vivid reminder that the universe's structure emerged gradually through the steady action of gravity. Supercomputers also help astronomers predict what future observations might reveal. By simulating the cosmic web in detail, scientists can forecast how many galaxies should exist in different regions of space, how gas should flow along filaments, and how clusters should evolve over time. When new telescopes conduct surveys of the sky, researchers compare the observations with these predictions. If the data match the simulations, confidence in the underlying cosmological model grows stronger. If they differ, scientists investigate whether new physics might be involved. This feedback between observation and simulation has become one of the central methods of modern cosmology. Telescopes gather enormous datasets describing the real universe. Supercomputers recreate those conditions in virtual form. Together they help astronomers understand how cosmic structure develops. As technology improves, simulations continue becoming more detailed. Future models may include trillions of particles and represent regions of space even larger than the observable universe. These simulations could reveal smaller filaments, more complex gas flows, and subtle interactions between galaxies and the surrounding cosmic web. Yet even the most advanced simulations must still rely on the same fundamental ingredients: gravity, dark matter, gas dynamics, and the initial fluctuations that existed in the early universe. From those ingredients emerges the intricate network connecting galaxies across billions of light years. Watching the simulated universe evolve offers a remarkable perspective. It shows that the cosmic web is not merely a pattern we observe today. It is the result of a long cosmic process unfolding over billions of years. Every map of the cosmic web shares one important limitation. No matter how detailed the observations become, the maps always stop at a certain distance. Not because astronomers lose interest, and not because the universe ends there, but because light from beyond that distance has not yet had time to reach us. The boundary is called the observable universe. It represents the farthest region of space whose light has arrived on Earth since the universe began expanding roughly 13.8 billion years ago. Because space itself has been stretching during that time, the most distant galaxies we can currently observe lie far farther away than 13.8 billion light-years. When cosmologists account for that expansion, the diameter of the observable universe comes out to about 93 billion light-years. Inside that enormous sphere, astronomers can study galaxies, filaments, clusters, and voids forming the cosmic web. Beyond it, everything becomes uncertain. The cosmic web that scientists map through galaxy surveys fills the observable universe almost everywhere they look. The same general pattern appears in every direction. Galaxies arranged along filaments, clusters forming at intersections, and vast voids between the strands. This consistency raises a natural question. If the web appears everywhere within the observable region, does it continue beyond the horizon as well? Most cosmologists suspect the answer is yes. There is no evidence suggesting that the cosmic web suddenly stops at the edge of the observable universe. Instead, the boundary simply marks the distance light has travelled since the Big Bang. Regions farther away certainly exist, but their light has not yet reached us. If those distant regions resemble the parts of the universe we can observe, the cosmic web likely extends far beyond our visible horizon. In fact, many models of cosmology suggest that the universe may be vastly larger than the observable portion. Some estimates propose that the full universe could be at least hundreds or even thousands of times larger than what we can currently see. Other theories allow for the possibility that the universe might be infinite. If that were the case, the cosmic web would not simply extend farther than our maps show. It would continue indefinitely, repeating its pattern of filaments and voids across an endless cosmic landscape. Of course, proving that possibility is extremely difficult. Observations are limited by the speed of light, and we cannot detect objects whose light has not yet had time to reach us. Still, astronomers have ways of investigating whether the universe might extend far beyond the observable horizon. One approach involves studying the geometry of space itself. The universe can have different possible shapes depending on how space is curved. If space were strongly curved, either positively like the surface of a sphere or negatively like a saddle, astronomers might detect certain patterns in the cosmic microwave background radiation. The cosmic microwave background is the faint afterglow of the early universe, emitted about 380,000 years after the Big Bang. This radiation fills the entire sky and carries subtle temperature variations that reflect the density fluctuations present in the young universe. By analysing these fluctuations, scientists can infer information about the overall geometry of the cosmos. So far, measurements from satellites such as WMAP and the Planck Observatory suggest that the universe is very close to geometrically flat. A flat universe does not necessarily mean the universe is infinite, but it allows that possibility. If space is flat and continues beyond the observable horizon, the cosmic web may stretch far farther than we can ever directly observe. Another interesting clue comes from the statistical uniformity of the cosmic microwave background. When astronomers examine this radiation across the sky, it appears remarkably consistent in every direction. The temperature variations are extremely small, only about 1 part in 100,000. This uniformity supports the idea that the universe on very large scales follows similar patterns everywhere. If the early universe contained similar density fluctuations across vast distances, gravity would have shaped those fluctuations into cosmic web structures throughout the larger cosmos. In other words, the filaments and clusters we see today may represent only a tiny portion of a much larger network. Even within the observable universe, astronomers continue discovering structures larger than previously known. Massive walls of galaxies, enormous superclusters, and extended filaments spanning hundreds of millions of light-years keep appearing in new surveys. Each time a new structure is mapped, scientists refine their understanding of how large cosmic formations can become. Yet these discoveries still fit within the broader expectation that the universe becomes statistically uniform on extremely large scales. In other words, while individual structures may grow enormous, the universe does not appear to contain structures that dominate indefinitely across all distances. Instead, the cosmic web forms a repeating pattern where filaments and voids appear at many locations across the cosmos. Another fascinating possibility involves something called cosmic inflation. Inflation refers to a brief period of extremely rapid expansion believed to have occurred during the earliest moments of the universe. According to inflationary theory, space expanded exponentially in a fraction of a second after the Big Bang. This sudden expansion could have stretched tiny regions of space to enormous sizes, potentially creating a universe far larger than the observable region we inhabit today. If inflation occurred as many cosmologists believe, the universe beyond our horizon might contain vast regions that we will never be able to observe. Each of those regions could contain its own cosmic web of galaxies forming over billions of years. In that sense, the cosmic web we observe might represent only one small patch within a much larger cosmic tapestry. Another idea explored by some cosmologists is the possibility of a multiverse, where different regions of space may contain slightly different physical conditions. In such scenarios, separate regions might develop their own structures, possibly including cosmic webs with varying properties. However, these ideas remain speculative and difficult to test. For now, astronomers focus primarily on mapping the cosmic web within the observable universe as accurately as possible. Future telescopes and surveys will extend those maps deeper into space. Projects such as the Euclid Space Telescope and the Vera C. Rubin Observatory aim to observe billions of galaxies across enormous cosmic volumes. These observations will help refine measurements of the cosmic web and reveal how its structure evolves over time. Even as the maps grow larger, the horizon of the observable universe will remain a fundamental boundary. Light from regions beyond that distance will not reach Earth until billions of years in the future. In that sense, the cosmic web continues beyond what we can currently see, but its most distant parts remain hidden from observation. Yet the structures we have already discovered are more than enough to inspire wonder. Filaments stretching across hundreds of millions of light years, clusters containing thousands of galaxies, voids so vast that entire superclusters could fit within them, and all of it woven into a network spanning tens of billions of light years. Wind the cosmic clock backward far enough, and the universe becomes almost unrecognizable compared with what we see today. The vast filaments of galaxies, the enormous clusters glowing with thousands of stars, and the huge voids separating them had not yet formed. Instead, the cosmos looked far simpler and far smoother, filled with a nearly uniform mixture of matter and radiation. Yet hidden within that early uniformity were the tiny seeds that would eventually grow into the cosmic web. These seeds appeared as extremely small differences in density across the young universe. Some regions contained just slightly more matter than others. The differences were almost unimaginably subtle. If you averaged the density of matter across large regions of the early universe, those fluctuations differed by only about 1 part in 100,000. From a human perspective, that seems far too small to matter. But over billions of years, gravity amplified those differences dramatically. The earlier stage of this story begins during the period shortly after the Big Bang, when the universe was still extremely hot and dense. During that time, matter and radiation were tightly coupled together in a glowing plasma. Photons constantly scattered off charged particles, making the universe opaque like a dense fog. Under those conditions, gravity could not yet gather matter into large structures. The constant interaction between matter and radiation prevented matter from collapsing into clumps. That situation changed about 380,000 years after the Big Bang. As the universe expanded and cooled, electrons and protons combined to form neutral hydrogen atoms. Once these atoms formed, photons no longer scattered as frequently. Light began travelling freely through space. This moment is known as recombination. The radiation released at that time still fills the universe today as the cosmic microwave background. Once the fog cleared, gravity could begin shaping matter more effectively. Dark matter had already begun forming small gravitational wells even earlier because it did not interact strongly with radiation. When ordinary matter was finally able to collapse, it started falling into those dark matter structures. The first clumps of matter gradually formed. Over tens of millions of years, these clumps grew larger as they attracted surrounding gas and dark matter. Eventually, the earlier stars ignited within these regions. Astronomers refer to this era as the cosmic dawn. These first stars were very different from the stars we see today. They likely formed from pristine hydrogen and helium gas left over from the Big Bang, with almost no heavier elements present. Many of these early stars were extremely massive and lived short, intense lives before exploding as powerful supernovae. Those explosions enriched the surrounding gas with heavier elements such as carbon, oxygen, and iron. As time passed, galaxies began forming around the densest regions of dark matter. These early galaxies were much smaller and less organized than modern galaxies. They contained only a fraction of the stars found in large galaxies like the Milky Way, but they represented the first visible lights tracing the emerging structure of the cosmic web. The web itself continued evolving during this period. Dark matter filaments gradually stretched between growing clumps of matter. Gas flowed along these filaments toward the densest nodes where galaxies were forming. Clusters began developing at the intersections of these strands. Meanwhile, the regions between filaments lost matter as gravity pulled material toward denser areas. These regions slowly expanded into the enormous void seen today. During the first billion years after the Big Bang, the cosmic web existed mostly as a network of dark matter and gas, with only a small number of young galaxies illuminating its structure. Observing this era directly is difficult because the galaxies were faint and distant. However, modern telescopes have begun detecting galaxies from this early period. Observations from instruments like the James Webb Space Telescope are revealing galaxies that formed only a few 100 million years after the Big Bang. These discoveries allow astronomers to glimpse the early stages of cosmic web formation. As billions of years passed, galaxies continued growing through mergers and the steady inflow of gas along cosmic filaments. Small galaxies combined to form larger systems. Clusters of galaxies gradually assembled at the intersections of filaments. The cosmic web became increasingly pronounced. At the same time, the universe itself continued expanding. Galaxies moved farther apart overall, even while gravity pulled matter together locally within clusters and filaments. This balance between cosmic expansion and gravitational attraction shaped the evolution of large-scale structure. During the Middle Ages of the universe, roughly 5 to 8 billion years after the Big Bang, the cosmic web reached a particularly active phase. Galaxies were forming stars at high rates. Mergers between galaxies were more common. Clusters continued growing as they attracted surrounding matter. The intergalactic medium flowed steadily along filaments, feeding star formation across many galaxies. Over time, however, the pace of galaxy growth began slowing. Star formation rates gradually declined as galaxies used up much of their available gas. Meanwhile, a new influence began shaping the evolution of cosmic structure. This influence is known as dark energy. Dark energy appears to drive the accelerated expansion of the universe. As dark energy became more dominant in recent billions of years, the expansion of space began accelerating. This acceleration makes it increasingly difficult for gravity to pull matter together across very large distances. As a result, the growth of cosmic structures has begun slowing. Clusters remain gravitationally bound, and galaxies within them will continue interacting. But the distances between clusters will gradually increase as cosmic expansion stretches the universe. Filaments connecting distant clusters may eventually become thinner as space expands between them. Despite this long-term trend, the cosmic web remains clearly visible today. Modern galaxy surveys reveal filaments stretching across hundreds of millions of light-years. Clusters containing thousands of galaxies glow brightly at their intersections. Vast voids fill the spaces between these structures. The web-like architecture created by gravity over billions of years continues shaping the distribution of matter across the observable universe. Another interesting aspect of studying the cosmic web across time involves looking at galaxies at different distances. Because light takes time to travel, observing distant galaxies allows astronomers to see earlier stages of cosmic history. Galaxies located billions of light years away appear to us as they existed billions of years ago. By comparing galaxies at different distances, scientists can trace how the cosmic web evolved over time. Nearby galaxies show the web as it appears in the present universe. More distant galaxies reveal earlier phases when structures were still forming. This ability to look back through cosmic time makes astronomy unique among sciences. Instead of relying solely on experiments, astronomers can directly observe different stages of the universe's history. Each distant galaxy provides a glimpse of an earlier moment in the formation of the cosmic web. Taken together, these observations show that the web did not appear instantly. It emerged gradually from the subtle density fluctuations present in the early universe. Gravity amplified those fluctuations over billions of years, guiding matter along filaments and into clusters. Voids expanded as matter drained away from them. Galaxies formed and evolved within this dynamic environment. Even now, the cosmic web continues changing slowly. Clusters merge, galaxies migrate along filaments, gas flows through the intergalactic medium. Yet these changes occur on timescales far longer than a human lifetime. From our perspective, the cosmic web appears almost timeless, but its story is still unfolding, and as astronomers think about how the web has evolved from the early universe to the present day, they inevitably begin wondering what its future might look like. Billions of years from now, the universe will still contain the cosmic web, but it will not look exactly the way it does today. The strands of galaxies stretching across space, the dense clusters at their intersections, and the vast voids between them will continue evolving under the influence of gravity and cosmic expansion. These changes will unfold slowly, far beyond the timescales of human history, yet they will gradually reshape the large-scale structure of the cosmos. To understand how the web might change, it helps to remember that the universe is still expanding. Since the Big Bang, space itself has been stretching, carrying galaxies farther apart over time. This expansion affects the cosmic web in subtle but important ways. Within galaxy clusters, gravity remains strong enough to hold galaxies together. Clusters are massive systems containing enormous amounts of matter, including dark matter that strengthens their gravitational pull. Galaxies inside these clusters orbit within the cluster's gravitational field and often interact with one another. Over time, these interactions can lead to mergers. When two galaxies merge, their stars usually pass by each other without direct collisions because the distances between stars are so large. However, their gravitational influence reshapes the galaxies involved. Gas clouds can compress, triggering bursts of star formation. Eventually, the galaxies settle into a new combined system. These mergers will continue occurring within clusters and galaxy groups for billions of years. Our own galaxy will participate in one of these events. The Milky Way and the Andromeda Galaxy are moving toward one another at roughly 110 kilometers per second. Astronomers estimate that the two galaxies will collide in about 4 to 5 billion years. The result will likely be a large elliptical galaxy, sometimes nicknamed Milkomeda. Although the collision will dramatically alter the appearance of the night sky from Earth, the solar system itself will probably remain intact. The distances between stars are so vast that direct stellar collisions are extremely unlikely. This merger represents a small example of a much larger process happening throughout the cosmic web. Galaxies along filaments gradually migrate toward clusters where gravitational interactions become more frequent. As time passes, clusters grow by absorbing nearby galaxies and smaller groups. Over billions of years, clusters may merge with neighboring clusters to form even larger structures. However, while gravity pulls matter together locally, another force is shaping the universe on larger scales: dark energy. Dark energy appears to be responsible for the accelerating expansion of the universe. Instead of slowing down over time due to gravity, the expansion of space has been speeding up for the past several billion years. This acceleration affects how structures in the cosmic web evolve. Within gravitationally bound regions such as clusters, dark energy has little immediate influence. Gravity remains strong enough to keep galaxies together. But between clusters, where gravity is weaker, dark energy gradually stretches space faster and faster. As a result, distant galaxy clusters will drift farther apart over time. Filaments connecting extremely distant clusters may eventually thin and stretch as the expansion of space pulls their endpoints away from each other. This does not mean the cosmic web will suddenly disappear. Instead, the web will slowly fragment. Clusters will remain intact as local islands of gravity, but the distances between them will continue increasing. Over very long timescales, billions or even trillions of years, the observable universe will change dramatically. Galaxies beyond our local region will gradually move farther away due to the expansion of space. Eventually they will recede so quickly that their light can no longer reach us. Astronomers sometimes describe this future as a cosmic isolation. In the distant future, observers in our galaxy may see only the galaxies within our own gravitationally bound cluster. All other galaxies will have moved beyond the cosmic horizon. From that perspective, the visible universe would shrink dramatically. The cosmic web would still exist across the larger universe, but its distant portions would no longer be observable. This long-term scenario depends heavily on the behavior of dark energy. At present, dark energy appears to have a constant strength over time, a property sometimes described by the cosmological constant. If dark energy continues behaving this way, the expansion of the universe will continue accelerating but not dramatically enough to disrupt gravitationally bound systems like galaxy clusters. In that case, clusters will survive as stable structures even as the distances between them grow. Some theoretical models, however, explore more extreme possibilities. One such scenario is known as the Big Rip. In the Big Rip model, dark energy becomes stronger over time, accelerating cosmic expansion at an ever-increasing rate. If that were to happen, the expansion of space could eventually overcome not only the gravitational binding of galaxy clusters, but also the forces holding galaxies themselves together. In the far future, clusters might dissolve, galaxies could break apart, and eventually even solar systems might be pulled apart by the expansion of space. However, current observations suggest that dark energy behaves more like a constant energy density rather than an increasing force. Most cosmologists therefore consider the Big Rip scenario unlikely. Under the more widely accepted model, the cosmic web will evolve slowly as gravity and expansion compete. Clusters will remain the largest stable structures in the universe. Within them, galaxies will continue merging and evolving. Filaments connecting nearby clusters may remain visible for long periods, but over time the stretching of space will make distant connections less significant. Another change that will occur over the next several billion years involves the gradual decline of star formation. Galaxies form stars by converting gas into new stellar systems. Over time, this gas supply becomes depleted. Without fresh gas flowing into galaxies, star formation slows. Many galaxies in the present universe already show signs of this slowdown. Large elliptical galaxies and clusters often contain mostly older stars and very little new star formation. As cosmic time progresses, more galaxies will transition into this quieter phase. The cosmic web will still exist structurally, but its galaxies may appear dimmer as fewer young stars form. Gas flowing along filaments may still feed some galaxies, particularly those outside dense clusters, but the overall pace of star formation will likely decline across the universe. Another important long-term change involves the growth of supermassive black holes. Nearly every large galaxy contains a black hole at its centre, with a mass millions or billions of times that of the Sun. When galaxies merge, their central black holes can eventually combine, producing even larger black holes. These mergers release enormous amounts of energy in the form of gravitational waves. Over cosmic time, the largest black holes may grow even larger through repeated mergers. Although these events occur within galaxies rather than across the entire cosmic web, they represent part of the ongoing evolution of structure within the web. Computer simulations of the far future suggest that clusters will eventually settle into stable configurations. After many billions of years, most of the galaxies within a cluster may merge into one enormous elliptical galaxy, surrounded by smaller satellite systems. These massive galaxies could dominate their clusters long after star formation has largely ceased. At that point, the cosmic web would appear much quieter than it does today. Clusters would remain as gravitational islands containing ancient stars. Filaments might persist but would gradually become less populated as galaxies migrate toward cluster centers. Voids would continue expanding as cosmic expansion stretches the distances between structures. From a human perspective, imagining these changes can feel almost surreal. The timescales involved are so vast that even the lifetime of the Earth represents only a brief moment in the story. Civilizations may rise and fall countless times, while the cosmic web slowly evolves. Stars will live and die, galaxies will merge, clusters will grow and settle, all while the overall expansion of the universe continues carrying distant structures farther apart. Yet even in the distant future, the fundamental pattern of the cosmic web will remain. Gravity will continue shaping matter into clusters and filaments. Dark energy will continue stretching space between those structures. The delicate balance between these forces will define the universe's large-scale architecture for billions or trillions of years to come. For now, however, the cosmic web remains vibrant and active. Galaxies continue forming stars. Clusters continue growing. Filaments continue channeling gas and galaxies across enormous distances, and observers on Earth can still see a universe filled with countless galaxies connected across billions of light years. Understanding the future of the cosmic web reminds us that the structure we observe today represents only one chapter in the long history of the universe. It emerged from the early fluctuations following the Big Bang, evolved through billions of years of gravitational interaction, and will continue changing far into the future. After travelling through such enormous scales of space and time, what does the cosmic web ultimately tell us about our place within the universe itself? Somewhere out there, far beyond the familiar glow of our own galaxy, the cosmic web stretches quietly across the universe. Filaments of galaxies span unimaginable distances, clusters shine like distant cities of stars, and enormous voids open between them like vast cosmic oceans. It is a structure so large that the mind almost refuses to grasp it all at once. Yet every galaxy we see in the night sky belongs to that same immense network. Throughout our journey tonight, we've gradually zoomed outward from the small corner of the universe we call home. We began with the simple question of how large the cosmic web really is, and along the way we discovered something remarkable. The universe is not arranged randomly. Instead, galaxies gather along enormous strands stretching across hundreds of millions of light years. Those strands intersect to form clusters containing thousands of galaxies. Between them lie cosmic voids so large that entire superclusters could drift through them without encountering much else. The cosmic web, in other words, is the grand architecture of the observable universe, and yet the story behind it begins with something incredibly small. Tiny fluctuations in the density of matter in the early universe, subtle differences that gravity slowly amplified over billions of years. From those faint irregularities emerged the intricate network of filaments and clusters that now stretches across tens of billions of light years. Gravity shaped the structure patiently. Dark matter provided the invisible scaffolding. Gas flowed along the filaments, feeding the formation of galaxies. Clusters gathered where multiple strands met. Voids expanded as matter drifted toward denser regions. Over time, the cosmic web took shape. Even now it continues evolving, though at a pace so slow that it appears almost timeless from our perspective. Galaxies migrate along filaments, clusters grow as they attract a nearby matter, voids gradually expand. And across unimaginable distances, light travels through this enormous structure, carrying messages from distant corners of the cosmos. Some of the photons reaching our telescopes tonight began their journey billions of years ago. They crossed filaments filled with galaxies, passed through clouds of faint intergalactic gas, and drifted across vast voids before finally arriving here. Every observation we make is therefore a glimpse into the universe's past. Astronomy, in a way, is the art of reading ancient light, but perhaps the most humbling realization comes when we consider our own place inside this web. The Milky Way is just one galaxy among hundreds of billions. It sits within a small group of neighboring galaxies. That group lies inside a larger supercluster, and that supercluster forms only one node within the enormous cosmic web stretching across the observable universe. From the perspective of the web itself, our galaxy is a tiny thread in a much larger tapestry. Yet that perspective also reveals something quietly beautiful. Despite the immense scale of the cosmos, everything we see belongs to the same connected structure. The stars above us, the distant galaxies visible through powerful telescopes, and the clusters mapped across billions of light years all share the same gravitational framework. The cosmic web binds them together, and within that web, the story of the universe continues unfolding. Galaxies are still forming stars, clusters are still gathering matter, filaments are still channeling gas and galaxies through the cosmic network. Even the vast voids play their role, shaping the flow of matter through the universe. The web is not frozen in time. It is a living structure evolving across billions of years. Looking far into the future, the cosmic web will change again. Dark energy will continue stretching space, gradually separating distant clusters. Galaxies within local groups may merge. Star formation will slowly decline as gas supplies diminish. Over immense spans of time, the universe may become quieter and darker. Yet the web itself will remain as the lasting imprint of gravity's work across cosmic history. All of this unfolds on timescales so vast that it can feel almost abstract. But the night sky offers a reminder that these structures are not just theoretical diagrams in scientific papers. They are real. Every star we see belongs to a galaxy. Every galaxy belongs to the cosmic web, and the light from those galaxies travels across that web before reaching us, which brings us back to where we began. You, sitting here at this moment, somewhere on a small planet orbiting an ordinary star inside an ordinary galaxy, and that galaxy drifting quietly along one filament of the cosmic web. It is easy to feel small when thinking about the scale of the universe, but it's also remarkable that beings on one tiny world have learned to see this enormous structure at all. Through centuries of curiosity, observation and patient science, humanity has pieced together the map of a universe spanning billions of light years. We have discovered that the cosmos is not random chaos. It is a network, a web connecting galaxies across space and time, and somewhere within that network, on a small spiral arm of the Milky Way, life has emerged capable of asking questions about the structure of the universe itself. That thought alone can feel quietly profound. Now, before we finish, let me ask you something again. Where are you listening from tonight? And what time is it in your part of the world right now? Perhaps it's late evening. Maybe the house is quiet, the lights are low, and the day is finally settling into rest. Or maybe it's earlier in the night, and you're simply taking a moment to step back and think about something larger than the routines of everyday life. Either way, I'm glad you joined me on this journey through the cosmic web. If you found this exploration calming or interesting, you might consider giving the video a like, subscribing to the channel, or sharing it with someone else who enjoys drifting through the universe before sleep. Science has a wonderful way of reminding us how vast the cosmos truly is, and sometimes thinking about that vastness can make the quiet moments of the night feel even more peaceful. Because right now, as the Earth turns slowly beneath the sky, The cosmic web continues stretching across the universe beyond our sight. Galaxies glow along distant filaments, clusters hold their ancient stars, voids drift in silent darkness between them, and somewhere along one small strand of that enormous structure sits our galaxy, carrying us gently through space. So wherever you are tonight, and whenever you happen to be listening, I hope the quiet immensity of the universe gives you a moment of calm. After all, the cosmic web will still be there, stretching across billions of light years long after we drift off to sleep.